Imagine a night sky stripped of every glimmer, every celestial body, every hint of light. No stars shimmer, no planets orbit, no distant galaxies punctuate the vast blackness. The universe lies in a frozen, cold emptiness, stretching infinitely, silent and unyielding. Once, it had been alive with energy, vibrant with the motion of stars and the dance of galaxies, but now it seems to have reached a point of finality, a stage where time itself feels suspended. Yet, questions linger. Will this cosmic expanse one day collapse in a cataclysmic blaze, tearing itself apart in a fiery maelstrom? Will it unravel quietly, fragmenting into nothingness? Or will it fade imperceptibly, dissolving into the infinite darkness? For centuries, scientists have pondered these fates, exploring theories ranging from a monumental big crunch to the slow, inexorable process known as heat death. The ultimate destiny of the cosmos remains one of the most haunting and fascinating mysteries of existence. At the dawn of the 20th century, the prevailing belief among scientists was that the universe was static, unchanging, eternal in its present form. Stars and galaxies were assumed to be fixed, suspended in a timeless void, each celestial body occupying a predetermined place. But this notion of a steady cosmos would be dramatically upended by the work of an American astronomer named Edwin Hubble. In the late 1920s, Hubble unveiled observations that would transform our understanding of the universe forever. It was not stationary, but expanding, stretching outward in all directions like a cosmic balloon inflating over billions of years. Before Hubble's revelations, most astronomers believed that the Milky Way comprised the entirety of the universe. The faint clouds of light scattered across the sky, known as nebula, were hotly debated. Were they mere clusters of gas within our galaxy, or entirely separate star systems? A Dutch astronomer, Willem de Sitter, had suggested that the universe could be expanding, but observational evidence was lacking. Even Albert Einstein, whose general theory of relativity had revolutionized physics in 1915, initially resisted the concept. When his equations implied that the universe should be dynamic, either expanding or contracting, he introduced a cosmological constant, an artificial adjustment, to preserve the notion of a static cosmos, later calling it the greatest mistake of his career. Hubble, stationed at the Mount Wilson Observatory in California, wielded the Hooker telescope, a 100-inch marvel that represented the pinnacle of observational technology in the 1920s. His mission, to probe the nature of distant nebulae. Were they part of the Milky Way or something far beyond? To answer this, he focused on a particular type of star known as a Cepheid variable. These stars pulsate with a rhythmic brightness, their cycles directly linked to their true luminosity. By comparing the intrinsic brightness of a Cepheid with how bright it appeared from Earth, Hubble could calculate astonishingly precise distances. What he discovered defied imagination. Some of these nebulae were far beyond the bounds of the Milky Way, distant galaxies in their own right, each brimming with billions of stars. The universe was unimaginably vast, far larger than anyone had conceived. But the revelation did not end there. By examining the light from these galaxies, Hubble noticed a curious effect. The light was stretched toward the red end of the spectrum, a phenomenon now called redshift. Much like the way the pitch of a siren drops as an ambulance speeds away, light waves elongate as their source moves farther from the observer. Every galaxy Hubble studied was receding from Earth, and, crucially, the farther away a galaxy was, the faster it seemed to retreat. This became known as Hubble's law, the first definitive proof that the universe was expanding. The implications were staggering. If the cosmos was expanding, it must once have been smaller, denser, unimaginably compact in the distant past. This realization planted the seeds for the Big Bang theory, proposing that the universe erupted from an almost infinitely dense and hot state, then expanded across time and space to its current enormity. Space and time were no longer fixed and eternal. They were fluid, dynamic, evolving with the universe itself. Questions multiplied. What had ignited this expansion? Would the cosmos continue stretching indefinitely, or would gravity one day reverse the motion, drawing everything back into a catastrophic collapse? Even Einstein, upon visiting Hubble in 1931 and witnessing the evidence firsthand, abandoned his cosmological constant, embracing the idea that the universe was alive, expanding, changing. Determining the precise rate of this expansion, known as the Hubble constant, has since been a challenge for astronomers, with the different methods yielding slightly divergent results. Yet the fundamental truth of Hubble's discovery remains unshakable. The universe is expanding, a cosmic ballet of galaxies drifting ever farther apart. This expansion hints at a profound narrative of origin and fate. If galaxies are now receding, it means that in the deep past, matter must have been concentrated into a single extreme point of density and temperature, a primeval seed of creation. The idea was first put forward in 1927 by a Belgian priest and astronomer, Georges Lemaitre, who imagined the universe beginning as a cosmic egg, a primeval atom whose explosion gave rise to all matter, energy, and space. Initially met with skepticism, Lemaitre's vision gained traction as evidence accumulated, culminating in the work of Hubble and others. The Big Bang theory gradually became the central narrative of cosmology, providing a window not only into the universe's origin, but also into its ultimate fate, a fate that may lie in the cold, silent expanse of an unlit cosmos, where stars no longer burn and the dark stretches on forever. Today, nearly a century after Edwin Hubble's groundbreaking observations, the Big Bang theory continues to dominate as the most widely accepted explanation for the origin of the universe. Modern telescopes and space observatories, most notably the Hubble Space Telescope, named in honor of the man whose work transformed cosmology, tirelessly gather data that reinforces and refines this theory. Hubble's discovery did not merely add a new chapter to astronomy, it rewrote the entire narrative of the cosmos. Before his observations, the universe was imagined as a static, relatively small collection of stars, mostly confined to the Milky Way galaxy. Hubble revealed a cosmos that was incomprehensibly vast and dynamically evolving, with galaxies moving away from each other in a grand cosmic dance that continues to this day. Thanks to Hubble, we now understand that the universe is expanding, a revelation that reshaped modern astronomy and physics. The Hubble Space Telescope, launched in 1990, has provided breathtakingly detailed images of galaxies billions of light years away, deepening our understanding of cosmic structures and the life cycles of galaxies. By measuring how fast these distant galaxies recede, astronomers have been able to quantify the expansion of the universe with ever greater precision. This research has even led to the astonishing discovery of dark energy, a mysterious force responsible for accelerating the expansion of the universe, one of the most profound mysteries in contemporary physics. Hubble's legacy stretches far beyond his own time. His observations laid the foundation for the field of cosmology, inspiring countless generations of scientists to probe the deepest questions about the universe's origin, structure, and ultimate fate. Before his discoveries, humanity's understanding of the cosmos was confined, almost provincial. Hubble's work shattered that limited perspective, revealing a universe in motion, one governed by forces that continue to puzzle and inspire scientists today. The implications of cosmic expansion were monumental. If galaxies are moving away from each other, the universe must have originated from a single immensely dense and hot point roughly 13 billion years ago. This realization crystallized into what we now call the Big Bang theory, offering the first coherent framework for understanding the history of everything from the smallest atoms to the largest galaxy clusters. How do scientists determine the speed at which galaxies are receding? The answer lies in the Hubble constant, a numerical value representing the rate of universal expansion. Hubble's initial calculations in the 1920s were crude by modern standards, but they were astonishingly accurate in principle. With advances in technology and observational methods, astronomers have refined this measurement, though debate remains over its exact value. The general consensus places it at approximately 70 kilometers per second per megaparsec. To translate, a megaparsec is roughly 3,260,000 light years. And this rate implies that for every 3 million light years of distance, a galaxy moves an additional 70 kilometers per second away from us. This incremental motion, when considered across billions of light years, accumulates into astonishing velocities, confirming the universe is expanding ever more rapidly the farther we look. The implications of cosmic expansion extend far beyond mere numbers. If galaxies are moving away from one another, what does the distant future hold? Scientists have proposed several scenarios, each tied to the behavior of the universe's expansion and the enigmatic influence of dark energy. The most widely accepted outcome, often called the Big Freeze, envisions an eternally expanding universe. As dark energy continues to drive galaxies apart, cosmic distances will grow so vast that galaxies will no longer interact. Stars will burn out, galaxies will drift into isolation, and the universe will cool into a dark, silent expanse over trillions of years. Another, even more dramatic scenario is the Big Rip. In this model, the expansion accelerates to such extremes that dark energy overwhelms all other forces, eventually tearing galaxies, stars, planets, and even atomic structures apart. This apocalyptic vision suggests a universe unraveling at the most fundamental levels, an ultimate cosmic disassembly where everything familiar is destroyed. A third possibility, less favored but still considered, is the Big Crunch. Here, the universe's expansion could gradually decelerate and reverse. Gravity would dominate, drawing all matter back together into a dense, hot singularity. Some theorists even propose that such a collapse could trigger another Big Bang, creating a cyclic model of endless cosmic rebirth. The movement of galaxies is not a mere celestial curiosity. It underpins our understanding of time, space, and existence itself. Observing the accelerating expansion of the universe provides compelling evidence for the Big Bang theory and reshapes our conception of cosmic history. Dark energy, the mysterious driver of this acceleration, constitutes roughly 70% of the universe's total content, yet remains virtually undetectable, except through its influence on space itself. Unlike ordinary matter or even dark matter, dark energy does not interact with light or other forces in ways we can directly measure, yet its presence dictates the universe's ultimate fate. For most of human history, the cosmos was assumed to be unchanging, eternal, and static. Edwin Hubble shattered that notion in 1929, demonstrating that every observed galaxy is receding and that their velocities increase with distance. This discovery challenged centuries of philosophical and scientific assumptions, sparking a paradigm shift in the understanding of the cosmos. The implications of Hubble's observations were staggering. If galaxies are speeding away, the universe must have had a beginning, a point of origin from which space itself has been expanding ever since. Over decades, astronomers debated how expansion would evolve. Gravity was expected to slow it down, potentially halting it entirely if the universe contained sufficient mass, possibly even reversing it into a catastrophic collapse. Others speculated that if matter was insufficient, expansion would continue indefinitely, though gradually slowing. But then, in the late 20th century, distant supernovae observations revealed an astonishing twist. The universe's expansion is not slowing, but accelerating. Dark energy, previously unimagined, dominates the cosmos, forcing galaxies apart at an ever-increasing rate, revealing a universe far stranger and more dynamic than anyone could have anticipated. Hubble's work, combined with decades of subsequent research, transformed our understanding of the universe from a static, closed system to a dynamic, ever-expanding cosmos, governed by forces still largely mysterious and unexplored. The study of cosmic expansion and dark energy continues to push the boundaries of physics, challenging the limits of human knowledge and promising to reshape not only our understanding of the universe, but potentially the technologies and philosophies that arise from comprehending its deepest secrets. The universe, in motion, ever expanding and accelerating, tells a story of scale, time, and mystery that continues to unfold across billions of light years, reminding humanity of the vastness of reality and the boundless scope of curiosity. However, in the year 1998, a groundbreaking discovery shook the foundations of cosmology. Two separate teams of astronomers, independently studying distant stellar explosions, known as Type 1a supernovas, stumbled upon evidence that would upend centuries of assumptions about the cosmos. These particular supernovas act as what scientists call standard candles. Their brilliance is predictable, a consistent lighthouse in the vast darkness of space. By observing how dim these explosions appeared from Earth, researchers could calculate their distances with remarkable precision. What they found was astonishing. The supernovas were far more distant than existing models predicted, revealing an unsettling truth. The expansion of the universe was not slowing down as expected. Instead, it was accelerating, pushing galaxies away from each other at ever-increasing speeds. This discovery pointed to a force that defies our everyday understanding of physics, a mysterious influence now called dark energy. Dark energy comprises the vast majority of the universe, yet it remains entirely invisible. We cannot touch it, measure it directly, or see it with any telescope. Its presence is inferred only through its effects on cosmic expansion. To explain dark energy, scientists have proposed several ideas, each more intriguing than the last. One of the earliest and simplest is the cosmological constant, a concept first introduced by Albert Einstein in his general theory of relativity. At the beginning of the 20th century, Einstein assumed the universe was static, neither expanding nor contracting. To align his equations with this belief, he introduced the cosmological constant, a repulsive force designed to counterbalance gravity. When Edwin Hubble's observations later proved that the universe was indeed expanding, Einstein abandoned the idea, famously calling it his greatest blunder. Yet, paradoxically, the cosmological constant returned to the forefront of physics after the discovery of dark energy. The cosmological constant suggests that empty space itself contains an intrinsic energy, sometimes referred to as vacuum energy. As the universe stretches, new space emerges, and with it more of this energy, which in turn continues to push galaxies apart. This elegantly matches current observations, but it raises profound questions. Why does this energy have the precise strength observed? Could it be the product of some deeper physical principle yet undiscovered? Another leading hypothesis is that dark energy is not constant but dynamic, evolving over time. This idea introduces a hypothetical force field known as quintessence. Unlike the uniform cosmological constant, quintessence could vary in strength across different regions of the universe and over cosmic epochs. If quintessence exists, it may explain why dark energy only became dominant relatively recently over the last few billion years of cosmic history. Yet, as compelling as this theory sounds, no direct evidence currently supports it, and physicists continue devising ways to detect or rule it out. A third possibility challenges our understanding of gravity itself. Perhaps dark energy is not a separate force, but rather an indication that gravity behaves differently across the immense scales of the cosmos. Alternative models, including theories involving extra dimensions or a fifth fundamental force, attempt to reconcile dark energy with a modified version of general relativity. Testing these ideas, however, is profoundly difficult. Gravity has been rigorously measured within galaxies and our solar system, and no violations of Einstein's equations have been observed at these scales. The stakes of understanding dark energy could not be higher. It is not a mere cosmic curiosity. It is the force that shapes the ultimate destiny of the universe. Depending on its properties, the future could unfold in vastly different ways. If dark energy remains constant or grows stronger, the universe will continue its accelerated expansion indefinitely. Galaxies will drift further apart, eventually becoming invisible to one another. Stars will exhaust their fuel, burn out, and leave a cold, dark universe dotted with black holes and dead stellar remnants. If dark energy increases dramatically, it could eventually overpower all forces, tearing galaxies, stars, planets, and even atoms apart in a catastrophic event, sometimes called the Big Rip. Some speculative theories suggest that dark energy might one day reverse its effect, halting cosmic expansion and causing a contraction, a big crunch, where all matter collapses back to a singular point, possibly triggering another cosmic cycle of expansion and collapse. To study dark energy, astronomers rely on indirect observational evidence. They meticulously examine distant supernovas to track how cosmic expansion changes over time. The cosmic microwave background, the faint radiation left over from the Big Bang, provides a snapshot of the early universe and hints at how dark energy has influenced its growth. Baryon acoustic oscillations, subtle patterns in galaxy distributions reveal the large-scale imprint of dark energy across the cosmos. Large-scale surveys, such as the Dark Energy Survey and the Euclid Space Telescope, map millions of galaxies to track the subtle effects of this enigmatic force. Despite decades of research, dark energy remains a cosmic puzzle. Its discovery has already transformed our understanding of the universe, yet its true nature eludes us. Will the universe expand endlessly into a frigid, starless future? Will it collapse in on itself, cycling through infinite expansions and contractions? Or does some hidden physics lie beyond our current comprehension, perhaps involving parallel universes or dimensions beyond the familiar three of space and one of time? Amidst these grand questions, the life cycles of stars continue with serene inevitability. Stars are colossal nuclear furnaces born from clouds of gas and dust. Over millions or billions of years, they fuse hydrogen into helium in their cores, releasing prodigious amounts of energy that illuminate the universe. Eventually, their nuclear fuel runs out and stars die, some fading quietly, others exploding in spectacular supernovas, seeding the cosmos with the elements necessary for planet and the next generation of stars. This eternal rhythm, intertwined with the invisible push of dark energy, shapes the universe on scales both immense and intimate, linking the destiny of galaxies to the fate of atoms in an endless cosmic dance. However, this fuel is not infinite. At some point, every star, regardless of its size or brilliance, will exhaust the energy that has sustained it for millions or even billions of years. The ultimate fate of a star hinges on its mass, determining whether it will fade quietly into obscurity or end its life in a cataclysmic, universe-shaking explosion. But before we explore these final acts of stellar life, it is crucial to understand the story of their beginnings, their growth, and the delicate balance that sustains them. Stars are born within immense clouds of gas and dust scattered throughout the cosmos, known as nebula. These ethereal clouds, often spanning light years in size, are composed primarily of hydrogen, the simplest and most abundant element in the universe, along with traces of helium and heavier elements. Gravity, the invisible sculptor of the cosmos, gradually pulls portions of these clouds together. As the particles cluster, the material becomes denser and hotter, and a remarkable transformation begins. Deep within these growing masses, temperatures skyrocket to millions of degrees, igniting nuclear fusion, the process that powers stars. This ignition marks the birth of a star, a self-luminous sphere of plasma poised to shine for millions or billions of years. The life of a star is defined by nuclear fusion, a process in which hydrogen nuclei collide and merge to form helium, releasing prodigious amounts of energy in the form of light and heat. This energy radiates outward, creating pressure that counterbalances the relentless inward pull of gravity. For most of its life, a star exists in a state of equilibrium called the main sequence, a stable phase where the push and pull forces are finely balanced. During this time, the star burns steadily, shining with a constant brilliance, its energy fueling the planets, moons, and potentially life forms in its system. However, this stability is temporary. As the star gradually consumes its hydrogen fuel, the core undergoes profound changes. These transformations eventually dictate the star's death, but the manner of its demise is intricately tied to its mass. Stars significantly smaller than our sun, known as red dwarfs, burn their fuel with extreme slowness, a patient and almost eternal process. Their energy output is low, their lifespans immense, trillions of years, far exceeding the current age of the universe, which is roughly 14 billion years. Because of this, no red dwarf has yet reached the end of its life. When the time finally comes, these diminutive stars will simply cool and fade, becoming cold, dark remnants called black dwarfs, silent witnesses to the eons. Stars like our sun of medium size follow a different path. The sun has already shone for nearly 5 billion years and has roughly the same amount of time remaining before its hydrogen reserves dwindle. As the fuel runs out, the sun will expand into a red giant, swelling so dramatically that it could engulf the inner planets, Mercury, Venus, and even Earth itself. During this grandiose phase, helium fusion will commence in the core, producing heavier elements such as carbon and oxygen. This stage is turbulent, marked by unstable processes that eventually lead to the shedding of the star's outer layers. These layers drift into space, forming a luminous shell known as a planetary nebula, a fleeting but breathtaking spectacle of cosmic art. What remains is the star's dense core, now exposed to the void. This remnant, a white dwarf, is a small yet incredibly dense object roughly the size of Earth, but possessing nearly the mass of the sun. Over billions of years, it will cool and dim, slowly fading into darkness, a quiet conclusion to a once vital presence. Massive stars, far larger than the sun, live fast and die dramatically. These cosmic giants burn their fuel at a furious pace, surviving only a few million years before exhausting their hydrogen. Their cores ignite successive layers of heavier elements, forming a complex, onion-like structure. Each new fusion stage generates energy, but only up to a point. When iron begins to accumulate in the core, the star approaches its ultimate fate. Unlike lighter elements, iron absorbs energy when fused rather than releasing it, causing the core to become unstable. In an instant, gravity overwhelms the weakened core, leading to a catastrophic collapse. This sudden implosion triggers a supernova, an explosion so powerful it can outshine entire galaxies for weeks. Supernovae are not merely destructive events, they are cosmic forges. The explosion scatters heavy elements such as gold, silver, and uranium across the galaxy, seeding the universe with the essential building blocks for new stars, planets, and life itself. The remnants left behind depend on the star's initial mass. Moderately massive stars leave neutron stars, astonishing objects of extreme density where a single teaspoon of matter weighs as much as a mountain. Some neutron stars spin rapidly, emitting beams of electromagnetic radiation that sweep through space like lighthouse beams, earning the name pulsars. For the most massive stars, the core collapse may continue into a black hole, a point in space with gravity so intense that not even light can escape, a final enigmatic monument to the star's life and death. From their humble beginnings in clouds of gas to their final acts as white dwarfs, neutron stars, or black holes, stars live extraordinary lives defined by the inexorable laws of physics, and their death is as magnificent and varied as their luminous existence. Every star is a storyteller of cosmic history, its light and matter echoing through the universe long after it has vanished from view. However, if the original star was truly massive, far larger than our sun, its core would continue collapsing under the relentless pull of gravity, eventually forming a black hole. This is a region of space so extreme that nothing, not even light itself, can escape its grasp. Black holes are some of the most enigmatic and fascinating objects in the universe, capable of bending time and stretching space to unimaginable extremes. Over time, all stars, regardless of their size, will exhaust their nuclear fuel. The most massive among them will end their lives in spectacular explosions, scattering their material across the cosmos, while smaller stars will quietly fade away, their remnants cooling over eons until they vanish into the cosmic darkness. Scientists predict that in the distant future, possibly in a time span unimaginably vast, numbers followed by 100 zeros of years from now, the universe will enter a state known as heat death. At that point, all stars will have long since died, and the cosmos will be a cold, silent, and empty expanse, with black holes slowly evaporating and the last remnants of light fading into the infinite void. The universe teems with stars, each a blazing sphere of incandescent gas illuminating the night sky. Yet, like all things in nature, stars have a life cycle. They are born, grow, change, and eventually die, transforming into entirely new celestial objects. The journey of a star can stretch across billions of years, and the final stage of its life depends primarily on its mass. Some stars swell into red giants before shrinking into white dwarfs, while others collapse into neutron stars, and the most massive may vanish into black holes. Every star begins its life within a nebula, a vast cloud of gas and dust drifting through space. Nebulae are often called stellar nurseries because they are the birthplaces of new stars. The gas in these clouds is overwhelmingly hydrogen, the most common element in the universe. Over millions of years, gravity gradually pulls the gas and dust together, forming denser regions. As the cloud compacts, temperatures rise, eventually creating a dense core known as a protostar. At this stage, the young star is still gathering mass and has not yet begun to shine. After millions of years, the protostar becomes hot and dense enough for nuclear fusion to ignite. Hydrogen atoms collide and fuse into helium, releasing tremendous amounts of energy that cause the star to shine. This marks the birth of a new star, which then enters the main sequence stage, the longest and most stable period of its life. A star in this phase continuously converts hydrogen into helium, producing heat and light that counteract gravity's inward pull. Small stars, like our Sun, remain in the main sequence for about 10 billion years, while much larger stars burn their fuel far faster, surviving only a few million years. Our Sun, for example, has spent approximately 4.5 billion years in this phase and is expected to continue for another 5 billion years before moving to the next stage. When a star exhausts the hydrogen in its core, it can no longer sustain the outward pressure from fusion, causing gravity to compress the star. Fusion shifts to the outer layers and the star expands dramatically, cooling as it does so, transforming into a red giant. Stars like the Sun can swell to nearly 200 times their original size, while more massive stars become red supergiants, even more enormous and imposing. Their cooler outer layers give them a reddish appearance, and they begin fusing heavier elements such as helium, carbon, and oxygen. Eventually, fusion ceases entirely, and the star undergoes a profound transformation. For stars roughly the size of the Sun, this next stage produces a white dwarf. After expelling their outer layers into space, creating glowing planetary nebula, the dense cores left behind form white dwarfs. These are incredibly compact objects, roughly the size of Earth but containing nearly the mass of the original star. A single teaspoon of white dwarf matter would weigh millions of tons. White dwarfs do not generate new energy. They radiate only residual heat, gradually cooling over billions of years until they fade into black dwarfs, cold remnants of stars that currently do not exist because the universe is only about 14 billion years old. Massive stars, many times the size of the Sun, follow a more violent path. They explode in supernova, among the most powerful events in the cosmos. When such a star's core collapses under gravity, it triggers a tremendous explosion, blasting outer layers into space and briefly outshining entire galaxies. What remains is an extraordinarily dense neutron star. Neutron stars just 10 to 20 kilometers across contain more mass than the Sun, so dense that a sugar cube-sized piece would weigh 1 billion tons. Many spin rapidly, hundreds of times per second, emitting beams of radiation called pulsars, which pulse detectable light across vast distances. Stars even more massive, at least 20 times the size of the Sun, collapse beyond the neutron star stage into black holes. These regions of space have gravitational pulls so extreme that nothing, not even light, can escape. Black holes are invisible, detectable only through their effects on nearby matter. At their cores lies the singularity, where mass is crushed into an infinitely small point, surrounded by the event horizon, the boundary from which nothing returns. Black holes vary in size. Stellar black holes form from individual stars, while supermassive black holes containing millions or even billions of solar masses occupy the centers of galaxies, including our Milky Way. Even now, stars continue to form, but this will not last forever. Hydrogen and helium, the building blocks of stars, will eventually be depleted. Scientists predict that in about 100 trillion years, the last stars will ignite. Afterward, the universe will enter the degenerate era, a time when no new stars can form. Existing stars will die, leaving behind cold, dark remnants like white dwarfs, neutron stars, and black holes. The cosmos will become a frozen, silent expanse, devoid of sunlight or warmth. During this time, occasional collisions between dead stars may release fleeting flashes of light. Black holes will slowly radiate energy through Hawking radiation, a process taking far longer than the current age of the universe. Over incomprehensibly long timescales, even these remnants will drift through space, cooling and fading. Black holes will stand as some of the last surviving objects in the cosmos, relics of massive stars long gone, lingering in the darkness until the final traces of the universe vanish. However, according to physicist Stephen Hawking, black holes are not eternal. He revealed a groundbreaking discovery. Black holes emit a faint form of radiation, now known as Hawking radiation. Over unimaginably long spans of time, trillions upon trillions of years, this radiation will slowly drain black holes of their energy, causing them to shrink gradually. Eventually, after periods far beyond the lifespan of any star, every black hole in the universe will vanish entirely. When the final black hole disappears, the universe will be left in a state of absolute emptiness. No stars, no galaxies, no black holes, only an endless expanse of void stretching in all directions. And yet, this is just the beginning of the universe's final chapter. Scientists call this ultimate state the heat death, or the big freeze. At this point, the universe will reach maximum entropy, a condition where energy is completely uniform and no work can be done. Entropy, in simple terms, measures disorder. As time marches on, energy disperses, systems even out, and all differences that drive change fade away. Once all energy is evenly spread, movement ceases, heat vanishes, and the possibility for anything new to occur disappears entirely. The universe will become a cold, dark, and lifeless place with no planets, no stars, no galaxies, only the quiet stillness of infinite emptiness. However bleak this scenario may seem, some theories suggest alternative outcomes for the distant future of the cosmos. The concept of the Big Bounce proposes that the universe might eventually collapse in on itself and trigger a new Big Bang, beginning the cosmic cycle anew. Quantum fluctuations, tiny spontaneous variations in empty space, could, over infinite time, give rise to an entirely new universe. And according to the multiverse theory, our universe might be just one among countless others, each with its own stars, galaxies, and perhaps even life. Yet, no matter how many possibilities exist, even these scenarios confront the inexorable march of time. Stars will burn out, black holes will fade, and the universe may ultimately settle into silence. The heat death, also called the Big Chill or Big Freeze, arises from the laws of thermodynamics. One day, all energy in the universe will be evenly distributed, leaving no usable energy to fuel motion, chemical reactions, or stellar activity. Stars will stop burning, planets will cease orbiting, and even atomic processes will halt. This does not mean the universe will freeze at a particular temperature. Rather, everything will settle into a uniform temperature, no matter how low. Scientists describe this state as thermodynamic equilibrium, where no energy flow is possible and nothing new can occur. If the universe is flat or hyperbolic in shape, or if a mysterious force called dark energy continues to drive eternal expansion, then this heat death scenario becomes inevitable. Over unimaginable stretches of time, the universe will cool steadily until it reaches a low, stable temperature where no physical process can function. The concept derives from the second law of thermodynamics, which states that entropy, the measure of disorder, always increases in an isolated system. In simpler terms, energy spreads, chaos grows, and eventually no useful work remains. Applied to the entire universe, this law predicts that over cosmic timescales, all energy differences will disappear and the universe will fall silent. The roots of this idea stretch back to the 18th and 19th centuries. In 1777, the French astronomer Jean-Sylvain Bailly suggested that planets generate internal heat that gradually fades, causing celestial bodies to cycle through heating and cooling phases. He speculated that Venus was too hot for life, Mars already too cold, and that eventually the cosmos would reach a state of complete equilibrium. By the 1850s, William Thomson, known as Lord Kelvin, expanded on these ideas. He realized that if energy spreads out and nothing replenishes it, all motion in the universe would eventually cease. Kelvin argued that the universe could not be infinitely old, for if it were, it would have already reached a lifeless equilibrium. Kelvin's work built on the earlier contributions of scientists such as Sadi Carnot, James Joule, and Rudolf Clausius. He described heat as a form of energy, intimately connected to mechanical work, and in 1852 he published a paper explaining the universal tendency of energy to dissipate, now recognized as the second law of thermodynamics. Over the next decade, others, including Hermann von Helmholtz and William Rankine, refined these ideas, applying them to cosmic scales. Kelvin imagined the universe like a giant clock. If left unwound, it would eventually stop. To restart it, an extraordinary force, a cosmic act of creation, would be required, leading to what became known as Kelvin's paradox. If the universe had existed forever, energy would already be evenly spread, stars would no longer shine, and heat differences would vanish. Yet we observe the universe still alive with energy and activity, revealing a tension between eternity and the finite nature of physical processes. Over the eons, the universe will continue to evolve toward this ultimate state. Stars will exhaust their fuel, black holes will evaporate, and atomic particles may eventually decay. Time itself, as we understand it, will lose meaning in this vast, frozen expanse. Only emptiness will remain, a silent testimony to the laws of physics and the relentless march of entropy, a cosmos gradually winding down, moving inexorably toward the cold, dark, eternal stillness that awaits at the end of everything. However, since stars continue to shine with brilliant light and vast differences in heat persist across the cosmos, It strongly suggests that the universe has not existed for an infinite amount of time. The warmth of a star, the glow of distant galaxies, and the constant motion of cosmic energy indicate a universe still in flux, far from any final stillness. Following the pioneering work of Lord Kelvin, both Hermann von Helmholtz and William Rankine recognized and credited him with conceptualizing the notion of heat death, a profound paradox that directly challenged the long-held belief in an eternal, unchanging universe. Helmholtz described heat death as the ultimate fate of all cosmic matter and energy, the final silent state where no thermodynamic work can be performed, while Rankine emphasized it as the end of every physical phenomenon, a cosmic stillness where motion ceases entirely. As decades passed, the scientific community explored a multitude of scenarios for the universe's distant future. By the late 20th century and into the early 21st century, newer theories emerged that expanded the scope of cosmic speculation. Some propose that if the universe continues its relentless expansion indefinitely, it might face a heat death, a slow fade into emptiness, or an even more violent end known as the Big Rip, where the fabric of space-time itself is torn apart, dismantling galaxies, stars, planets, and even atoms. If the universe possesses a positive cosmological constant, a measure tied to the rate of its expansion, then instead of cooling to absolute zero, it may settle into a near-zero temperature, leaving no energy available for meaningful work, a kind of cosmic stasis where the engine of the universe grinds to a halt. The theory of heat death envisions a universe that has been teeming with activity since the Big Bang, filled with galaxies, stars, black holes, and cosmic filaments that drive the flow and transformation of energy. Yet, energy continues to circulate today, confirming that the universe has not reached its final state. Looking far ahead into timescales almost impossible to comprehend, the cosmic landscape will transform in unimaginable ways. Enormous black holes destined to grow to gargantuan sizes will slowly evaporate through a process known as Hawking radiation. A black hole with the mass equivalent to an entire galaxy, roughly 100 billion times the mass of our Sun, would require a duration of about 1, followed by 100 zeros years to vanish entirely. Even larger black holes could take an inconceivable 1, followed by 10 to the power of 60 years to disappear. After these titanic structures fade away, the universe will enter the so-called dark era, a period in which virtually nothing happens. It will be sparsely populated by an almost imperceptible, ultra-cold gas of minuscule particles, such as photons and leptons. Energy will be vanishingly small, time will stretch over mind-boggling intervals, and motion, as we understand it, will cease. Yet some theorists speculate that the cosmos might undergo a second inflationary phase, a sudden and rapid expansion, reigniting the dynamics of space-time. Others suggest that if our universe resides in a temporary metastable energy state, it could collapse into a different, lower energy configuration, fundamentally altering the structure of everything we know. Should none of these possibilities occur, heat death remains the inevitable endpoint, an eternal, motionless expanse where nothing occurs, an endless cosmic void. Even then, there is a final, almost unimaginable possibility. Over extraordinarily long periods, statistical anomalies known as thermal fluctuations could trigger a tiny local decrease in entropy, potentially giving rise to new structures or even a new universe. The Planché recurrence theorem suggests that if one waits long enough, potentially 1 followed by 56 zeros years, quantum randomness could generate a fresh universe, effectively rebooting cosmic history. The ultimate destiny of the universe remains deeply uncertain. If heat death prevails, all motion, energy, and life will vanish, leaving a dark, empty void. Yet, with the enigmatic role of quantum fluctuations, even this seemingly final state might be only temporary. Entropy, the measure of disorder and energy dispersal, is central to these debates and remains one of the most perplexing concepts in physics, particularly when applied on a universal scale. Max Planck, the eminent physicist, once remarked that the notion of the entropy of the universe is not entirely meaningful, as it lacks a precise definition. In 2008, physicist Walter Grandindy highlighted humanity's limited knowledge of cosmic processes, noting that defining the universe's entropy is premature, especially when the cosmos has never been in perfect thermodynamic balance. Likewise, Laszlo Tisza argued that assigning an entropy value to a system outside equilibrium is inherently impossible. Hans Adolf Bajdahl went further, stating it is entirely unjustified to treat the universe as a closed thermodynamic system, like a sealed laboratory container of gas. Giovanni Gallavotte pointed out the lack of a universally agreed definition of entropy for non-equilibrium systems, and the challenge only intensifies in chaotic, ever-changing conditions. Elliot H. Lieb and Jacob Ingverson observed that although non-equilibrium entropy is widely theorized, no definition has been universally accepted, while Peter Landsberg cautioned that applying thermodynamics to the entire universe without deeper understanding is misleading and speculative. A 2010 analysis reinforced these doubts, emphasizing that the entropy of gravitational fields remains unknown and difficult to measure. However, it also revealed a striking insight. Supermassive black holes dominate the universe's total entropy, contributing more than any other cosmic structure. Physicist Lee Smolansky expanded on this, explaining that gravity fundamentally shapes the universe's energy distribution. Unlike typical systems where energy loss slows motion, gravitational systems accelerate as they lose energy, leading to greater complexity and fragmentation rather than equilibrium. Recent experiments confirm that even closed systems can sustain non-equilibrium steady states, where entropy redistributes without violating thermodynamic laws, highlighting the intricate dynamics of isolated systems. The concept of universal entropy remains an open question. Scientists suspect the existence of non-equilibrium entropy, but have yet to define or measure it comprehensively. Observations of black holes and gravitational behavior continue to challenge classical thermodynamic assumptions, revealing one of modern physics' most compelling mysteries. The ultimate fate of the universe stands as one of cosmology's greatest enigmas. This scientific field, dedicated to understanding the origin, structure, and destiny of the cosmos, has generated several theories about how the universe might evolve. These hypotheses are grounded in observation and physical principles, not myth or religion. Some posit a finite universe with a definite beginning, while others suggest a universe that has always existed in some form. Resolving the question of the universe's beginnings and trajectory remains among the most profound pursuits in science. In the early 20th century, astronomer Edwin Hubble made a discovery that transformed our understanding. Between the 1930s and 1950s, he observed galaxies moving away from each other, implying the universe is expanding. This led to the Big Bang Theory. The universe began from an extremely dense, hot state roughly 13,787,000,000 years ago. Subsequent measurements of expansion rate, cosmic matter, and energy properties have reinforced this model. Today, most scientists agree that the universe is geometrically flat, meaning straight lines extend indefinitely without bending toward or away from each other, and that cosmic expansion will continue forever, carrying galaxies, stars, and cosmic structures into an ever-deepening, expansive future. However, to truly unravel the mysteries of the universe's birth and ultimate destiny, scientists must delve into a vast array of interconnected phenomena. They examine not only the movement and distribution of galaxies across unimaginable distances, but also the very shape and geometry of the cosmos itself. Among the most enigmatic aspects of this study are two substances that continue to elude complete understanding: dark matter, an invisible form of mass that exerts gravitational influence, and dark energy, a mysterious force that drives the accelerated expansion of the universe. The ability to even begin predicting the universe's future first emerged in 1915, when Albert Einstein unveiled his revolutionary theory of general relativity. His equations described with remarkable precision how gravity shapes space and time on the grandest scales imaginable. Over the following decades, scientists discovered multiple mathematical solutions to Einstein's equations, each suggesting radically different possibilities for how the universe might evolve. In 1922, a Russian mathematician named Alexander Friedmann proposed several solutions that hinted the cosmos could be expanding. Just a few years later, in 1927, a Belgian physicist named Georges Lemaitre refined these ideas, showing that one of these solutions implied the universe had originated from a single, unimaginably dense and compact point. This theoretical event would later be called the Big Bang, marking the explosive birth of everything we know. The first observational confirmation came in 1929, when Edwin Hubble studied Cepheid variable stars in distant galaxies. By measuring their brightness and pulsation rates, he calculated distances and found that galaxies were receding from us in all directions. This observation provided irrefutable evidence that the universe was expanding, fundamentally changing humanity's understanding of the cosmos. In 1927, Lemaitre formally proposed the concept that would evolve into the Big Bang theory. But science thrives on debate, and in 1948, Fred Hoyle presented a competing idea, the steady-state theory. According to this theory, the universe, while expanding, maintained a constant average density because new matter was continuously created, implying a cosmos with no beginning or end. For years, these theories competed for acceptance, until 1965, when two scientists, Arno Penzias and Robert Wilson, stumbled upon cosmic microwave background radiation. This faint, omnipresent radiation, the afterglow of the early universe, provided powerful evidence supporting the Big Bang theory and gradually led the scientific community to embrace it as the most accurate description of cosmic origins. Curiously, Einstein himself had originally favored a static universe, believing it neither expanded nor contracted. To reconcile his equations with this assumption, he introduced the so-called cosmological constant. Yet when Hubble demonstrated that the universe was indeed expanding, Einstein famously called the introduction of the constant his biggest blunder, acknowledging that the cosmos did not conform to his original expectations. A central concept in predicting the universe's ultimate fate is the density parameter, often denoted by the Greek letter omega. This number determines whether the universe will continue to expand forever, halt its expansion, or eventually collapse back on itself. If omega equals 1, the universe is flat. If greater than 1, it is closed. If less than 1, it is open. The total amount of ordinary matter, combined with dark matter and dark energy, heavily influences these outcomes, which is why generations of astronomers have meticulously measured omega. In 1998, observations of distant exploding stars known as supernovae revealed a stunning surprise. The universe's expansion was accelerating rather than slowing. This discovery pointed to an unseen force, now called dark energy, driving galaxies apart at ever-increasing speeds. While its exact nature remains elusive, one possibility is that dark energy represents a form of energy permeating all of space, constantly pushing the universe to expand faster. Researchers continue to investigate whether this force remains constant over time or evolves alongside the cosmos, with some hypothesizing links to a primordial quantum field from the universe's infancy. To probe these profound mysteries, scientists employ cutting-edge instruments such as the Euclid Space Telescope, the Nancy Grace Roman Space Telescope, and the James Webb Space Telescope, as well as powerful ground-based observatories. Together, these tools allow researchers to refine measurements, test theoretical predictions, and explore how dark energy might shape the universe's long-term trajectory. The fate of everything depends on three key factors: the universe's geometry, the abundance of dark energy, and the equation of state, which describes how dark energy evolves as the cosmos expands. Evidence gathered from billions of years of cosmic history suggests that starting around 7.5 billion years after the Big Bang, the expansion of space began accelerating, supporting the possibility of an open universe that may continue expanding indefinitely. Yet, the story is nuanced. Data from the Wilkinson Microwave Anisotropy Probe indicate that the universe is either perfectly flat or extremely close to flat. If omega exceeds 1, space is curved like a giant sphere, where the sum of angles in a triangle exceeds 180 degrees and lines eventually converge, a geometry called elliptic. In such a closed universe, gravitational forces would eventually halt expansion. Once halted, the cosmos would begin contracting, drawing all matter inward until it collapsed into a singular point, an event termed the Big Crunch, which mirrors the Big Bang in reverse. Every galaxy, star, and particle would be pulled together in a final cosmic convergence, signaling the dramatic end of a universe that began as a single infinitesimal point. However, if dark energy possesses sufficient strength, it could counteract the force of gravity entirely, driving the universe into a state of endless expansion, even in a universe that would otherwise be closed. Today, the most widely accepted framework for understanding this cosmic behavior is known as the Lambda Cold Dark Matter Model, or Lambda CDM. According to this model, dark energy constitutes roughly 68% of all the energy in the universe. Within this framework, for gravity to regain dominance over dark energy and cause the universe to collapse back in on itself, the amount of matter present would need to be approximately 17 times greater than what current observations indicate. If the density parameter, often denoted as omega, is less than 1, the structure of space itself is altered in a dramatic way, taking on a curvature that resembles a saddle. In this hyperbolic geometry, the angles inside a triangle sum to less than 180 degrees, and lines that begin close together diverge relentlessly over time. In such an open universe, gravity simply cannot halt the ongoing expansion. Instead, the universe continues to grow, with galaxies and other celestial objects drifting ever farther apart. Should dark energy maintain its dominance, the expansion will not merely persist at a constant rate, it will accelerate, pushing galaxies so far from one another that, in the distant future, they may become invisible from each other. These various scenarios paint multiple possible fates for the universe: a collapse into a final singularity, eternal expansion into the void, or some other outcome that challenges our imagination. Even in a universe devoid of dark energy, a negatively curved or saddle-shaped cosmos would continue expanding indefinitely. Gravity would slow this process, but never halt it entirely. The introduction of dark energy, however, creates a remarkable transformation. Instead of steady growth, the expansion accelerates over time. If dark energy continues to drive the cosmos outward, two extreme outcomes become conceivable. One is known as heat death, or the Big Freeze, a state in which the universe becomes so vast and diffuse that all heat and energy are evenly distributed, rendering life and activity impossible. The other, even more dramatic, is called the Big Rip, where dark energy eventually overpowers not only gravity, but the fundamental forces that hold atoms and molecules together. In such a scenario, galaxies, stars, planets, and even the tiniest particles would be torn asunder, leaving only dispersed radiation drifting through the void. Conversely, if the universe possessed a negative cosmological constant, a form of energy that counteracts expansion, even an open universe would eventually cease expanding and collapse inward in a phenomenon known as the Big Crunch. In this fate, all matter and space itself would fall back together, potentially setting the stage for another cycle of cosmic birth and rebirth. The geometry of the universe hinges on the concept of critical density, a delicate balance between the pull of gravity and the push of expansion. When the universe's average density matches this critical threshold, space is considered flat. In a flat universe, triangle angles add up to exactly 180 degrees, and parallel lines neither converge nor diverge. Observations from the Wilkinson Microwave Anisotropy Probe reveal that our universe is extraordinarily close to this flat condition, with a margin of error smaller than half of 1%. Without dark energy, a flat universe would expand forever, gradually slowing as gravity counters the outward motion, never stopping entirely, yet never accelerating. With dark energy, however, the expansion initially decelerates under gravity's influence, but eventually accelerates, resulting in a fate similar to that of an open universe: perpetual growth. Scientists have long recognized that the universe's destiny depends heavily on its density. Current evidence overwhelmingly suggests that the universe will continue expanding indefinitely. If this projection holds true, it will ultimately culminate in the Big Freeze. In this scenario, temperatures steadily decline, and the universe becomes an ever larger, lifeless void. Stars will continue forming, ranging from 1 trillion to 100 trillion years. Yet as the cosmic supply of gas dwindles, new star formation will cease. Existing stars will gradually burn out, leaving a universe growing colder and darker. Over unimaginably long timescales, black holes will emerge as the dominant structures. Yet even these titanic objects are not eternal. Through Hawking radiation, black holes slowly evaporate, vanishing into nothingness over spans of time beyond ordinary comprehension. Some theoretical models suggest that, given infinite time, rare fluctuations could induce temporary reversals of entropy, creating brief, random bursts of order within the otherwise chaotic void, though such ideas remain speculative. The Hubble constant quantifies the universe's rate of expansion. Currently, this expansion is sufficient to increase distances between galaxies, yet it is not strong enough to tear them apart. Should the expansion accelerate indefinitely, however, it could ultimately destroy all matter. At some distant point, even atoms and fundamental particles would be ripped apart, leaving only isolated energy, approaching a singularity-like state, an ultimate cosmic breakdown. A particularly extreme variation involves phantom dark energy, an enigmatic form capable of accelerating expansion even beyond conventional predictions. If such energy dominates, the Big Rip could arrive sooner than anticipated, abruptly and violently terminating the universe. The Big Crunch hypothesis offers a strikingly different vision. It suggests that just as the universe began with a massive explosion, the Big Bang, it could one day reverse course, with expansion halting and contraction beginning. If sufficient matter and energy exist, gravity might overcome the outward expansion, drawing all galaxies, stars, planets, and space itself inward. The cosmos would collapse into a highly compact, dense point, possibly a singularity, resembling the universe's state before the Big Bang, closing the cycle of cosmic evolution. However, scientists remain far from certain about what the ultimate fate of the universe will be. Observations show that the cosmos is expanding, and not just at a steady pace, but accelerating, a phenomenon that casts doubt on the likelihood of a dramatic collapse known as the Big Crunch. Yet, these observations cover only an infinitesimal fraction of the universe's immense lifespan, leaving room for possibilities that stretch far beyond our current comprehension. One of the most captivating theories suggests that the universe might experience endless cycles of growth and collapse, a rhythm of cosmic birth, death, and rebirth. In this vision, after collapsing into a minuscule, incomprehensibly dense state during a big crunch, the universe could ignite a new Big Bang, giving rise to another universe, and this cycle might have repeated countless times before, destined to continue indefinitely. This notion is known as the cyclic or oscillating universe theory. However, this elegant concept encounters a formidable challenge from the laws of physics. The second law of thermodynamics, which dictates that disorder or entropy must always increase over time, seems to contradict the possibility of a perpetually reborn universe. Each cycle would accumulate entropy, ultimately leading to a state of complete uniformity where no useful energy exists, a scenario known as heat death. Faced with this contradiction, many scientists have shifted their focus away from the cyclic model. A nuanced variation called the Big Bounce theory offers an alternative. Rather than succumbing to an ultimate collapse, this theory proposes that a mysterious force, potentially rooted in quantum mechanics, could prevent the universe from condensing into a singularity. Instead of ending, the universe would rebound, initiating a fresh expansion phase. If this is the case, our current universe might have emerged from the remnants of a predecessor, suggesting a cosmos without a true beginning or end, only an endless sequence of rebirths. Moreover, some modern interpretations of the Big Bang challenge the notion of an initial singularity entirely. Quantum mechanics implies that the universe may have tunneled into existence, arising from an unknown precursor rather than an infinitely dense point. This perspective aligns more comfortably with quantum principles, which often resist the notion of absolute singularities. Despite the elegance of these theories, current evidence strongly indicates that the universe is expanding too rapidly to collapse, and yet, gaps in our understanding remain vast. The behavior of dark energy, the invisible force accelerating the cosmos, is still largely speculative. Early in cosmic history, during a period known as cosmic inflation, a different form of dark energy dominated, only to dissipate later, revealing that dark energy's nature might be far more complex than current models assume. It is even conceivable that dark energy could evolve unpredictably, triggering cataclysmic consequences. One dramatic hypothetical event tied to dark energy is called the Big Slurp. This scenario arises from the possibility that the universe resides in a false vacuum, a temporary and unstable energy state. If the vacuum were to suddenly transition into a lower energy true vacuum, The resulting shift could fundamentally alter the universe's fabric. Central to this idea is the Higgs field, an invisible energy field pervading space, which has distinct energy levels similar to an electromagnetic field. If our universe occupies a higher energy false vacuum, it could abruptly tunnel to a lower energy state in a process called vacuum decay. Such a transformation could alter the fundamental constants governing physics, dismantling the forces that hold atoms together and destabilizing the very structure of matter, energy, space, and time. This change could happen instantaneously in localized regions, obliterating structures within those areas without warning. Remarkably, the Big Slurp would not annihilate the entire universe. Galaxies more than 4,200 megaparsecs, roughly 13 billion light-years, apart are receding faster than light due to cosmic expansion. Since the bubble of vacuum decay cannot spread faster than light, most of the universe would remain untouched. For context, the observable universe, the portion visible from Earth, extends about 46 billion light-years in every direction, while the full universe is likely far larger. To assess which scenarios are plausible, researchers weigh the universe by measuring contributions from ordinary matter, radiation, dark matter, and dark energy to its overall density. They also test models against real-world observations, how galaxies cluster, the behavior of distant supernovas, and minute variations in the cosmic microwave background, the faint afterglow of the Big Bang. The Big Crunch, a dramatic and historic theory, envisions a universe that, after billions of years of expansion, halts and begins to shrink. Gravity would pull everything together, from galaxies to atoms, collapsing all matter into a superdense, superheated point, reminiscent of the Big Bang's initial conditions. Stars would ignite violently under compression, and temperatures would rise to unimaginable extremes. Time and space themselves could cease in the final instant. Yet, some theorists propose that this collapse might not mark the universe's ultimate end. The Big Bounce theory suggests that at the extreme point of contraction, the universe could rebound, triggering another Big Bang and perpetuating a cosmic cycle of expansion and contraction. For centuries, scientists debated whether the universe would end in a collapse or continue expanding indefinitely. In the late 1990s and early 2000s, observations of distant supernovas and the cosmic microwave background revealed a startling truth. The universe's expansion is accelerating, making collapse increasingly improbable. This discovery earned the 2011 Nobel Prize in Physics, reshaping our understanding of the cosmos. Ideas about cosmic collapse are not new. In the 17th century, English scholar Richard Bentley questioned Isaac Newton about the universe's fate. If gravity draws all matter together, would not stars eventually collapse into a single point? If the universe is infinite, wouldn't forces cancel, preventing collapse? This early thought experiment, Bentley's paradox, prefigured modern Big Crunch theories. Today, we understand that stars move constantly and the universe is expanding, preventing such a collapse. Albert Einstein, initially believing the universe was static, collaborated in 1917 with Dutch astronomer Willem de Sitter to test whether his general relativity equations could accommodate a stationary cosmos. De Sitter's calculations indicated a simplified universe could indeed exist within this framework. While initially convincing, further discoveries revealed that the universe is far from static, instead behaving in ways that continue to challenge the boundaries of human understanding. The ultimate fate of the universe, whether through endless expansion, cyclic rebirth, catastrophic vacuum decay, or some yet undiscovered process, remains one of the most profound mysteries in science. Each observation, each theory, each glimpse into the cosmos pushes the limits of knowledge, revealing a universe far stranger, more dynamic, and more enigmatic than ever imagined. However, they soon ran into a perplexing twist of cosmic logic, a variant of a conundrum known as Bentley's paradox, which immediately threw their understanding of the universe into question. At first glance, Einstein's equations of general relativity seemed to support a static, unchanging cosmos, a comforting idea that fit neatly with the prevailing astronomical consensus of the time. Yet, paradoxically, the very mathematics of his theory implied that the universe could never be truly still. According to relativity, the cosmos was inherently dynamic, either relentlessly expanding or inexorably contracting. This created a profound contradiction. For decades, astronomers had looked at the night sky and assumed it was a fixed, eternal tableau, immune to change. To reconcile his theory with the widely accepted notion of a static universe, Einstein introduced a mysterious counteracting force, a form of anti-gravity that would balance the relentless pull of matter on itself. He called it the cosmological constant, a precise mathematical addition to his field equations designed to prevent the universe from collapsing under its own gravity. It was an elegant fix, a subtle nudge to the cosmos to stand still, yet entirely artificial, imposed on the natural flow of relativity. The universe, however, had a surprise in store. In the 1920s, Edwin Hubble, working at the Mount Wilson Observatory, embarked on a meticulous survey of distant galaxies. By measuring their distances and comparing them with the phenomenon known as redshift, where light stretches toward the red end of the spectrum as objects move away, he uncovered a startling truth. Earlier, astronomers Vesto Slipher and Milton Humason had studied these redshifts, but it was Hubble who synthesized their work with his own distance measurements to reveal a breathtaking cosmic pattern. The farther a galaxy lay from Earth, the faster it receded into the void. Hubble mapped this relationship using data from 46 galaxies and formulated what is now called the Hubble constant. His initial estimate, 500 kilometers per second per megaparsec, overshot the value accepted today, yet the deeper implication was even more profound. The universe was expanding, dynamic, alive, and utterly unlike the static cosmos long imagined. When Einstein learned of Hubble's discovery, he immediately recognized the truth hidden within his own equations. The cosmological constant, once a crutch to maintain a static universe, was unnecessary. Relativity alone predicted an expanding or contracting cosmos. In retrospect, Einstein famously described the introduction of the cosmological constant as the greatest blunder of his life. By 1931, he journeyed to meet Hubble personally, expressing gratitude for laying the groundwork for modern cosmology. From that moment, the notion of a static universe was consigned to history, and the scientific community embraced the revelation of an ever-expanding cosmos. Yet, even an expanding universe posed new questions. Some theorists proposed that the cosmos might not grow indefinitely. The Big Bounce hypothesis suggested that expansion could eventually reverse, causing the universe to collapse back to a dense, compact state, primed for a rebirth, a new Big Bang. This implied a cyclical nature to existence itself, an endless sequence of cosmic births and deaths. In 1931, Einstein himself entertained the idea that our universe might not be unique, hypothesizing that a previous universe had collapsed in a cataclysmic Big Crunch, sparking the birth of our own universe in a new Big Bang. In this framework, reality itself becomes a perpetual cycle of creation, expansion, contraction, and renewal, repeating without end. Decades later, physicists expanded upon this concept, exploring models of cyclic universes with increasing sophistication. One prominent modern theory, the episodic model, proposed by Paul Steinhard, suggested that the Big Bang was not a singular event, but the result of a collision between two enormous parallel cosmic structures called branes, existing in a higher dimensional space. According to this idea, our universe exists on one such brane, floating in a multi-dimensional expanse. When these branes collide, it triggers cycles of cosmic destruction and rebirth. Quantum fluctuations preceding the collision set the initial conditions for matter, radiation, and the large-scale structure of the universe. Over billions of years, the universe expands and evolves into the familiar cosmos we inhabit today, only to eventually contract again, beginning the cycle anew. A mysterious force known as dark energy may play a central role in this cycle, influencing the expansion of the universe and addressing long-standing puzzles, such as the apparent flatness of space and the absence of magnetic monopoles predicted by earlier models. One of the major challenges for cyclic models has always been entropy, the natural accumulation of disorder. Without a solution, repeated cycles would eventually lead to heat death, a lifeless, static cosmos. The episodic model proposes that a slight net expansion with each cycle prevents entropy from reaching catastrophic levels, allowing the cosmos to continue indefinitely. Yet many mysteries remain. The very nature of branes is tied to string theory, itself a deeply theoretical framework still lacking experimental confirmation. Furthermore, some scientists argue that the extreme conditions of a big crunch might obliterate the delicate structures needed to sustain the next universe. While cosmic inflation and vacuum fluctuations are well studied, no particle physics model currently fits seamlessly into this cyclic framework. Another vision of a repeating universe emerged from Roger Penrose, who developed the theory of conformal cyclic cosmology, CCC. In this scenario, the universe continues expanding until all matter decays into pure energy, transforming the cosmos entirely into light. At this point, conventional concepts of size and time dissolve, and the universe resets itself, mirroring the conditions that preceded the Big Bang. The end of one cosmic era becomes the beginning of another, continuing a seamless cycle. Penrose, together with Gorodon, proposed that subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang, might carry evidence of these previous cycles, with uniform temperature rings acting as remnants of gravitational waves from earlier universes. This vision of a cycling cosmos stretches the imagination, merging mathematics, observation, and speculative physics into a tapestry of endless creation. Each expansion and contraction, each birth and death of universes becomes part of a greater rhythm, a cosmic heartbeat echoing through the infinite corridors of time, suggesting that the universe is not merely a singular event, but a chapter in an eternal story of rebirth and transformation. However, as of the year 2020, scientists have yet to uncover conclusive evidence supporting the conformal cyclic cosmology theory, often abbreviated as CCC. Despite its compelling and imaginative framework, this model remains a subject of heated debate within the scientific community. Critics argue that for the transitions between cosmic cycles to occur, all particles in the universe would somehow need to shed their mass completely as the universe ages, a requirement that many physicists consider highly improbable. This specific challenge remains a central point of contention, casting a shadow of skepticism over the theory. Yet Roger Penrose, the physicist behind CCC, continues to advocate for it with unwavering conviction. He points to curious circular patterns observed in the cosmic microwave background radiation, patterns he interprets as the residual echoes of gravitational waves generated by black hole collisions in a preceding cosmic cycle. According to CCC, the universe we inhabit is merely one aeon in an endless series of cosmic epochs, each beginning with a new Big Bang and eventually fading into another, perpetuating an eternal rhythm of creation and decay. While theories such as CCC captivate the imagination and stretch the boundaries of our understanding, they remain largely speculative. Researchers are tirelessly seeking more tangible evidence, driven by the hope of unraveling the profound mysteries surrounding the past, present, and potential future of the universe. Should any of these bold models prove accurate, it would imply that the cosmos we perceive today is merely a single chapter in an infinite narrative, a story that has been unfolding for timescales beyond human comprehension. Parallel to CCC, loop quantum cosmology offers another radical perspective on the universe's origins and evolution. This framework challenges the conventional Big Bang narrative by suggesting that the universe might not have emerged from a sudden singular explosion. Instead, it may have undergone an ongoing cycle of contraction and expansion, creating what scientists describe as a quantum bridge connecting different phases of existence. In this model, the behavior of space and time diverges sharply from classical physics. While these quantum effects are imperceptibly subtle in the vast expanse of a stretched-out universe, they become profoundly influential when the universe contracts to an incredibly minuscule size, approaching the Planck scale. At this juncture, a new quantum force dominates, overpowering the familiar pull of gravity and preventing the universe from collapsing into a singularity as predicted by Einstein's general theory of relativity. By eliminating singularities, loop quantum cosmology forces a re-evaluation of fundamental cosmic questions, including the puzzling uniformity observed across vast regions of space. Instead of a singular Big Bang, this model introduces the concept of a big bounce, where the universe contracts to a small yet non-zero size before expanding again, repeating this cycle indefinitely. Scientists employ the concept of effective dynamics to model these extreme cosmic events, with advanced computer simulations demonstrating the method's effectiveness. Even in scenarios where significant quantum uncertainty arises in later stages of the universe, the simulations remain largely accurate, capturing the universe's overall behavior with remarkable fidelity. In addition, researchers have explored the possibility that the current expansion of the universe, driven by dark energy, could one day reverse, initiating a contraction phase instead. If a hypothetical energy field called quintessence is responsible for dark energy and its strength diminishes below zero, the universe could start shrinking within the next 100 million years. Physicists such as André Agius and Paul Steinhardt argue that this scenario aligns well with the concept of a cyclic universe, envisioning an endless succession of expansion and contraction phases. They estimate that this contraction phase could last for approximately 1 billion years before a new cycle of expansion begins. In contrast, physicist Paul Davies proposed an alternative fate for the cosmos, in which contraction continues unabated until a complete collapse occurs, an event known as the Big Crunch. According to this model, such a catastrophic collapse could transpire roughly 100 billion years from now. During this contraction, galaxies would merge and the temperature of space would rise as light waves become increasingly compressed. Approximately 500,000 years before the final collapse, stars would collide due to extreme proximity, causing radiation to reach levels hotter than even the coolest stars, leading to their evaporation. The process would intensify, eventually consuming even the largest and most massive stars around 100,000 years before the universe's final moment. In the last fleeting minutes, temperatures would soar to unimaginable extremes, breaking apart atoms themselves. All matter would be drawn into colossal black holes, ultimately crushing everything into an infinitesimally tiny, unimaginably dense, and blisteringly hot point, echoing the state of the universe before the Big Bang. Some theorists propose that this might trigger yet another Big Bang, giving birth to a brand new universe, further fueling the notion of an eternal cyclical cosmos. Such scenarios push the boundaries of human understanding, challenging fundamental notions of time, existence, and the universe's ultimate fate. Could the cosmos indeed be eternal, rebirthing itself endlessly through cycles of expansion and contraction? Or is it destined to reach a final, immutable state, never to change again? While these questions remain unanswered, ongoing research in quantum physics and cosmology continues to expand the horizons of knowledge, drawing humanity ever closer to deciphering the enigmatic narrative of the universe. Adding to the spectrum of cosmic possibilities is the chilling hypothesis known as the Big Rip. In this scenario, the universe does not simply expand forever. Instead, it stretches at an accelerating pace until galaxies, stars, planets, and even the smallest atoms are torn apart. The Big Rip represents one of the most extreme predictions regarding the universe's ultimate destiny. If this catastrophic outcome proves correct, every structure in existence, from the tiniest subatomic particles to the largest cosmic formations, will eventually be obliterated in a dramatic, all-encompassing cosmic unraveling. The Big Rip would not occur instantaneously, but would unfold through a series of devastating stages, each progressively more violent. Current scientific estimates suggest that if this scenario is realized, it could happen roughly 20 billion years from now. Initially, the universe's expansion would continue as observed today, with galaxies drifting ever farther apart. But over time, the acceleration would intensify, stretching cosmic structures to the breaking point, heralding a gradual yet inevitable destruction of everything we perceive as stable in the cosmos. However, as dark energy's influence grows ever stronger, the universe will undergo a transformation so profound that the familiar cosmic landscape we take for granted will begin to dissolve. Galaxies that for billions of years were bound together by the gentle but persistent tug of gravity will start to drift apart, no longer able to resist the relentless push of this mysterious force. The intricate cosmic web, that vast network of galaxies and clusters stretching across unimaginable distances, will slowly begin to fray, each thread pulling taut before finally snapping. A few billion years before the universe reaches its final catastrophic moments, dark energy will reach a level of dominance so extreme that it will overwhelm the gravitational bonds even inside individual galaxies. The Milky Way, our own stellar home, along with every other galaxy scattered across the cosmos, will begin to fragment. Stars that once traced orderly paths through galactic orbits will be flung into the abyss, scattering like cosmic shrapnel into the void. As the Big Rip draws nearer, the pull of dark energy will grow so immense that it will surpass even the gravitational forces holding solar systems together. Our sun, once the steady anchor of our solar system, will no longer maintain its serene command over its planets. Earth and its neighboring worlds will drift aimlessly, untethered, cast adrift into a vast, starless expanse. Planets will float in the darkness, lost and isolated, severed from the warmth and light that sustained life and structure. Even after galaxies and solar systems are gone, dark energy will continue its inexorable advance. It will intensify to a point where even the stars themselves, once brilliant and enduring, cannot withstand its force. The sun, along with all stars across the universe, will be torn apart, their atoms scattering across the emptiness like cosmic dust carried on an unstoppable wind. Yet the devastation does not stop there. Eventually, the relentless expansion driven by dark energy will reach the atomic scale. Planets, moons, and all solid matter will succumb, broken down atom by atom. The strong nuclear force, the invisible bond that holds atomic nuclei together, will be powerless against the growing strength of dark energy. In the final moments before the Big Rip, even protons, neutrons, and electrons, the fundamental building blocks of all matter, will be ripped apart. What remains will be a universe filled with solitary particles drifting endlessly through an infinite void. At this stage, the universe will be utterly unrecognizable. There will be no galaxies, no stars, no planets, no life, and no structures to trace the history of the cosmos. Only emptiness, stretching without end, will mark the aftermath of this catastrophic unraveling. The universe itself will have been fragmented into raw, isolated energy, leaving behind nothing familiar or structured. The concept of the Big Rip emerges from our current understanding of dark energy, yet the nature of this force remains one of the deepest mysteries of modern cosmology. Scientists are diligently exploring its properties, striving to determine whether this apocalyptic scenario is a real possibility or a distant theoretical curiosity. Some researchers speculate that dark energy might evolve over time, potentially weakening rather than intensifying. In such a case, the universe could experience a different fate entirely. For example, if dark energy fades, cosmic expansion might slow, possibly reversing into a dramatic contraction known as the Big Crunch, where all matter collapses back into a single, dense point. Conversely, if dark energy remains constant, the universe could continue expanding at a steady pace, avoiding the extreme violence of the Big Rip altogether. This scenario, called the Big Freeze, envisions galaxies drifting apart while remaining intact, slowly cooling and darkening over trillions of years until the cosmos becomes a frozen, silent expanse. If the Big Rip scenario is accurate, we currently live in a comparatively stable epoch. Immediate danger is non-existent, as the event would not occur for at least 20 billion years, far beyond the remaining lifespan of our sun, which is projected to burn for another 5 billion years. Yet, exploring such extreme possibilities provides scientists with crucial insight into the mechanics of the universe. Each discovery about dark energy brings us closer to predicting the universe's ultimate fate billions of years into the future. Phantom energy, a particularly exotic variant of dark energy, is central to the Big Rip hypothesis. Unlike gravity, which diminishes as objects move apart, phantom energy grows stronger as space itself expands. The larger the universe becomes, the more aggressively phantom energy stretches and tears, a force that grows with the expansion it drives. This concept originates from precise mathematical equations describing the energy density of space. Scientists quantify these properties using a value called the equation of state. When this number falls below -1, the energy is classified as phantom energy. The danger of phantom energy lies not in gentle expansion, but in domination. While ordinary dark energy allows galaxies to drift apart over immense timescales, phantom energy accelerates expansion to extremes, eventually overpowering every known force in the universe. If this energy continues to strengthen, the cosmos faces a Big Rip scenario, a cataclysm in which space stretches too far, too fast for any structure to survive. The stages of this unfolding catastrophe are predicted with chilling detail. About 1 billion years before the final rupture, the universe's expansion would be clearly evident. Galaxies would retreat from each other at accelerating rates, yet for now, their internal structures, stars and systems, would remain intact. Over time, this gradual, relentless pull would intensify, setting the stage for the eventual dismantling of all cosmic architecture, from galaxies to atoms, until only the scattered remnants of particles remain, drifting through eternal emptiness. However, over time, the sky would begin to look increasingly empty, a vast canvas stripped of its familiar patterns as distant galaxies vanished from view, their light stretching and fading beyond recognition. 60 million years before the Big Rip, the influence of phantom energy would grow overwhelmingly strong. Entire galaxies, once bound tightly by the invisible chains of gravity, would begin to unravel. Stars and planets, previously held together in cosmic communities, would drift apart like islands torn from a sinking archipelago, separated by an ever-expanding cosmic ocean. 3 months before the Big Rip, the Milky Way itself, the galaxy that cradles our solar system, would start to come undone. The force of phantom energy would overwhelm even the immense gravitational grip of black holes, rendering them powerless. Stars, planets, and the remnants of solar systems would scatter into the darkness, leaving the night sky unrecognizable, a chaotic tableau of isolated, wandering stars. 30 minutes before the Big Rip, the destruction would reach the scale of individual planetary systems. Planets would break free from the bonds of their stars, drifting helplessly into the void. Even Earth, once securely tethered to the sun, would be flung into the cold, empty reaches of space, its orbit severed and its environment doomed. 1 second before the Big Rip, the cataclysm would penetrate the atomic level. Molecules, atoms, and even the subatomic particles that form the fabric of reality would be torn apart. Electrons would be ripped from their nuclei, atomic structures would collapse, and the fundamental building blocks of matter would dissolve. After this instant, nothing would remain. The very structure of space would expand so violently that reality itself might be shredded, leaving a universe devoid of galaxies, stars, planets, or atoms, only a vast, ever-expanding void. If this ultimate fate is truly written in the cosmos, is there any hope to prevent it? Scientists remain uncertain because phantom energy defies conventional physical laws. Yet, there are theoretical possibilities. Phantom energy could be a temporary phase, a fleeting phenomenon rather than a permanent cosmic force. Should its effects slow or reverse, the Big Rip might never occur, and the universe could stabilize or take a different trajectory entirely. Alternatively, future breakthroughs in physics might reveal unknown forces capable of counteracting phantom energy. Discoveries in quantum mechanics or string theory could uncover a hidden cosmic equilibrium, a balance that preserves the universe in ways we cannot yet comprehend. Some speculative theories even entertain the notion that intelligent civilizations could escape to other universes, traversing wormholes, manipulating space-time, or creating artificial realms where life could persist despite the destruction of their original cosmos. Currently, galaxies are already receding from one another due to the ongoing expansion of the universe, a process that has been unfolding for over 13 billion years. Gravity has been their tether, holding them together against this drift. But if dark energy intensifies, it will overcome gravity, forcing galaxies apart at unprecedented speeds. The first visible sign of the Big Rip would be galaxies retreating faster than ever, their once beautiful clusters fading and stretching into obscurity. Over time, even the Milky Way would lose its neighbors, including Andromeda, and galaxies themselves would start to fragment. Stars that once spun in elegant spirals and luminous clouds of gas would be flung apart, no longer held by gravity, cast into the endless void. As the expansion accelerates, stars themselves would succumb. The delicate balance between gravity pulling inward and nuclear fusion pushing outward would collapse under the onslaught of dark energy. Stars would swell, fracture, and ultimately explode. Massive stars like the Sun would lose their outer layers, scattering their material across the void. Dense stellar remnants such as white dwarfs, neutron stars, and black holes might be shredded before they can fully form. Even black holes, once considered the universe's ultimate survivors, would be stretched beyond endurance. With the demise of stars, planets would lose their gravitational anchors, drifting helplessly through space. Moons, comets, and asteroids would follow suit, unbound and lost to the void. Earth, bereft of the sun's gravity, would spin into a frozen, airless darkness, oceans solidifying, life ending abruptly. Other planets in the solar system, from Jupiter to Saturn, would endure the same catastrophic fate, eventually reduced to dust as dark energy's grip tightened. As the universe neared its final moments, even atoms, the core components of matter, would not survive. Nuclei, electrons, and the bonds forming molecules and compounds would be torn apart. Fundamental elements, once considered the building blocks of existence, would vanish. Reality itself would dissolve, leaving only scattered, isolated particles in a featureless void. In the final seconds, the universe would be shredded at speeds exceeding light itself, and in an instant, everything that ever existed would be obliterated. Galaxies, stars, planets, atoms, every structure and every particle would vanish, leaving nothing but infinite emptiness. Time, space, and the laws of physics might lose all meaning, an incomprehensible cessation of existence. Yet despite the terrifying inevitability suggested by these theories, uncertainty remains. The universe's fate hinges on the elusive nature of dark energy. If it remains constant rather than escalating, the cosmos could continue to expand more slowly, approaching a frigid dark state in a scenario known as the heat death, where time stretches endlessly over a silent, lifeless universe. However, if dark energy continues to grow stronger, the possibility of a catastrophic cosmic event known as the Big Rip becomes more real. In this scenario, the very fabric of the universe could be torn apart, with galaxies, stars, planets, and eventually atoms themselves pulled violently asunder. To unravel this mystery, astronomers tirelessly observe distant galaxies, chart the movement of celestial bodies, and study the cosmic microwave background radiation, the afterglow of the Big Bang, hoping to detect subtle clues about how dark energy behaves over time. Some scientific models suggest that dark energy might gradually weaken, acting as a natural break that prevents the universe from tearing itself apart. Other theories venture further, proposing that unknown aspects of physics beyond our current understanding could radically alter the cosmic trajectory, making any prediction provisional at best. Black holes, on the other hand, stand as some of the most enigmatic and formidable objects known to science. Often described as cosmic vacuum cleaners, they exert a gravitational pull so powerful that not even light can escape once it crosses a certain invisible threshold. Their immense density and extreme gravity make them both mesmerizing and terrifying, challenging our understanding of space, time, and matter. But beyond their immediate danger, black holes may hold keys to the universe's ultimate fate. Will they accelerate cosmic destruction, or might they endure long after other structures have faded, serving as the final remnants of existence itself? To answer these questions, we must explore the nature of black holes, how they form, and the ways they interact with the cosmos. A black hole is a region in space where gravitational forces become so extreme that escape becomes impossible. The boundary that defines this point of no return is called the event horizon. Anything that crosses it, whether star, planet, or photon, is lost forever, swallowed by a singularity, a point of infinite density where the laws of physics as we know them cease to apply. Black holes are born from the deaths of massive stars. Stars generate light and heat through nuclear fusion, a process that converts hydrogen into helium, releasing immense energy. This energy creates outward pressure that balances the inward pull of gravity. Yet, when a star with a mass several times that of our Sun exhausts its nuclear fuel, it can no longer resist its own gravity. The core collapses, and if the mass is sufficient, a black hole forms. There are multiple types of black holes. Stellar black holes, formed from the collapse of massive stars, typically contain a few times the mass of the Sun. Supermassive black holes reside at the centers of galaxies and can reach billions of times the Sun's mass. Intermediate black holes occupy the size range between stellar and supermassive, remaining elusive and largely mysterious to scientists. Primordial black holes, hypothetical remnants from the earliest moments of the universe, are even smaller and entirely theoretical, yet they offer tantalizing possibilities about cosmic history. Despite differences in size and origin, all black holes share one defining trait. Once something falls in, it never returns. The influence of black holes on the universe is profound. Far from being mere destructive forces, they play a crucial role in shaping galaxies and regulating cosmic processes. At the heart of nearly every galaxy, including the Milky Way, lies a supermassive black hole. These giants act as cosmic governors, influencing star formation by consuming material and releasing powerful jets of energy. These jets can sweep away gas and dust, temporarily halting the birth of new stars and redistributing matter across vast distances. Black holes are also the engines behind some of the universe's most violent and energetic phenomena. Gamma-ray bursts, among the brightest explosions observed, occur when massive stars collapse into black holes. The collision of black holes generates gravitational waves, ripples in space-time that scientists can detect on Earth, opening an entirely new window into the cosmos. Quasars, formed when black holes devour immense quantities of matter, shine brighter than entire galaxies, showcasing the incredible energy that can emerge from these dense objects. Even the recycling of matter and energy in black hole activity contributes to cosmic evolution. While black holes consume stars and gas, not all material is trapped indefinitely. Some is ejected in the form of high-energy jets and radiation, seeding distant regions with the building blocks for new stars, planets, and potentially life itself. In this way, black holes embody both destructive and creative forces, influencing the universe on scales that stretch across millions of light years. Looking at the bigger picture, the universe is expanding. Galaxies drift apart, and over unimaginable timescales, the cosmos will grow increasingly empty and cold. Physicists have long debated the ultimate fate of this expansion, proposing several possible scenarios. In the heat-death model, the universe continues to expand forever. Energy spreads ever thinner, stars exhaust their fuel, and matter slowly drifts into obscurity. In such a future, black holes may be among the final bastions of matter, slowly consuming what remains before eventually evaporating through Hawking radiation, leaving a cold, dark, and quiet cosmos. Their presence, paradoxically, ensures that even as stars fade, remnants of the universe's history endure, silent witnesses to a once vibrant cosmic symphony. Black holes may be feared for their voracious appetites, yet they are also guardians of cosmic order, shaping galaxies, recycling matter, and perhaps, in the farthest reaches of time, standing as the last structures in an otherwise lifeless universe. Their study offers not only insight into the violent and extreme, but also a glimpse into the ultimate destiny of all that exists. However, even black holes, the most formidable and enigmatic objects in the cosmos, are not eternal. Across the incomprehensible expanse of time, they gradually lose energy through a subtle, mysterious process known as Hawking radiation, named after the renowned physicist Stephen Hawking, who first proposed this phenomenon in the year 1974. This radiation is imperceptibly slow, almost glacial in its effect. A black hole with the mass of our sun would take trillions upon trillions of years, far beyond any human comprehension, to evaporate completely. Yet, inexorably, even the largest supermassive black holes, which dominate the centers of galaxies and weigh billions of times more than the sun, will eventually vanish. This process stretches across a timescale so vast that it dwarfs the current age of the universe, which is roughly 14 billion years. When the final black hole dissolves, all that will remain is a cold, empty cosmos, a silent expanse punctuated only by faint remnants of radiation, ghostly whispers of what once existed. Another possibility for the ultimate fate of the universe involves gravity reversing the cosmic expansion, eventually pulling all matter back together in a colossal implosion known as the Big Crunch. In such a scenario, black holes could merge into a singular, incomprehensibly massive entity, consuming everything in its path. Some theoretical models suggest this might trigger a cosmic rebirth, a phenomenon called the Big Bounce, where the universe explosively ignites in a new Big Bang, beginning the cycle of creation anew. In contrast, a scenario known as the Big Rip envisions the expansion of the universe accelerating so violently that not only galaxies, but also individual atoms are torn apart. In this unimaginable future, even black holes could not survive, for the very fabric of space-time itself would be shredded. Each of these end-of-universe possibilities hinges on phenomena we only partially understand, most notably dark energy, the mysterious force driving galaxies ever farther apart. Currently, humanity exists within the Stelliferous era, a period characterized by the radiant glow of countless stars, providing light, warmth, and energy throughout the cosmos. This era began over 13 billion years ago, shortly after the initial explosion of the Big Bang. Within it, stars of all sizes and colors fill galaxies, from small, dim red dwarfs to colossal, searingly hot blue giants. They are born within immense clouds of gas and dust, live for millions to billions of years, and eventually reach the end of their life cycles. Massive stars erupt in titanic supernova explosions, leaving behind neutron stars or black holes, while smaller stars, like our own sun, expand into red giants before collapsing into white dwarfs, faint, dense remnants of their former brilliance. As time marches on, the universe will gradually grow darker. In roughly 100 trillion years, the last star will exhaust its fuel and fade away. With most hydrogen, the essential ingredient for star formation, depleted, no new stars will ignite. What remains will be the remnants: white dwarfs slowly cooling into black dwarfs, neutron stars quietly fading, and black holes, the universe's most voracious predators, continuing to dominate the cosmic landscape. These black holes will consume the scattered debris left in space, reigning supreme over a universe stripped of luminous life. Eventually, the cosmos will enter the black hole era, a time when no stars shine and black holes constitute the primary structures in existence. These entities, so powerful that not even light can escape their gravitational grasp, will slowly evaporate through Hawking radiation. The smaller a black hole, the faster this loss occurs, while the largest supermassive black holes will endure for periods so immense that conventional numbers fail to capture them. One could imagine a small black hole with the mass of the Sun taking 10 to the power of 64 years to vanish completely. A supermassive black hole at the heart of a galaxy could persist for 10 to the power of 100 years or more. As each black hole fades, it releases a final burst of energy, leaving behind a void where nothing remains to sustain light, heat, or life. When the last black hole finally disappears, the universe will reach what scientists call heat death, a state of absolute darkness and stillness, where no energy exists to drive new structures or forms of life. It will be a vast, cold, silent void, unimaginably different from the vibrant star-filled universe we inhabit today. The black hole era will represent the final chapter of cosmic evolution, a realm ruled not by light, warmth, or activity, but by the lingering echoes of gravitational power, fading imperceptibly into eternity, marking the ultimate destiny of everything that once shone in the heavens. Imagine a universe without light. With no stars left to shine, the cosmos would plunge into utter darkness, a silent expanse stretching in every direction. The only faint glimmers would come from the slow, almost imperceptible glow of black holes evaporating over inconceivable spans of time. Galaxies, once brilliant clusters of stars and cosmic activity, would be gone. Over billions upon billions of years, galaxies would gradually dissolve, their stars and planets flung into the emptiness by the relentless tug of gravity. The once bustling hubs of cosmic life, swirling with energy and motion, would fade, leaving behind only solitary black holes, drifting like ghostly sentinels in an endless void. Matter, from wandering asteroids to decayed planets, and even the final surviving particles, would inexorably spiral into these immense gravitational traps. As the universe continues its expansion, even these last black holes would slowly diminish, shrinking as they release their energy in an almost imperceptible wisp of radiation. When they finally disappear, all that would remain is a cold, stretched emptiness, a universe stripped bare of all matter and light. Beyond this profound stillness, the fate of the cosmos becomes a question of speculation. Some theories suggest it will continue expanding eternally, a silent, empty expanse stretching into infinity. Others speculate that quantum fluctuations might one day spark the birth of a new universe, a cosmic reset, a chance for creation to start anew, as if the universe itself were turning a page in an endless book of existence. The journey of black holes merging is no less dramatic, though it unfolds over millions or even billions of years. Most mergers begin with two black holes orbiting each other, remnants of massive stars, each at least 20 times the mass of our Sun, that ended their lives in explosive supernovae. If these progenitor stars were already in a cosmic dance before their deaths, their collapsed remnants, now black holes, continue this orbit, forming a binary black hole system. Slowly, almost imperceptibly, the black holes draw closer. They lose energy in the form of gravitational waves, faint ripples traveling through the fabric of space and time, waves predicted by Albert Einstein's theory of relativity. As the black holes spiral inward, their motion accelerates, reaching speeds that approach a significant fraction of the speed of light. The gravitational waves they emit intensify, spreading across the universe. On Earth, scientists capture these echoes of distant collisions using instruments like LIGO, the Laser Interferometer Gravitational Wave Observatory, and Virgo. These detectors can sense the faint tremors of black hole mergers occurring millions or billions of light years away. Eventually, the two black holes collide in a moment of unimaginable violence, merging into a single, more massive black hole. The energy released is staggering. In mere fractions of a second, more energy can be unleashed than all the stars in the observable universe combined. This energy radiates outward as gravitational waves, shockwaves rippling across the cosmos, bending and stretching space itself. Even after the merger, the newly formed black hole is not immediately at rest. It wobbles and vibrates like a bell struck by an invisible hand, in a phase known as the ring down, emitting gravitational waves until it achieves a smooth, stable form. Once settled, it remains a dominant force, capable of growing by absorbing gas, dust, or even other black holes. Black hole mergers are not just spectacular cosmic events, they are gateways to understanding the universe. They confirm Einstein's century-old prediction of gravitational waves, offering proof of general relativity. They allow scientists to probe the behavior of space and time under extreme conditions. They reveal hidden black holes invisible to conventional telescopes, and may hold keys to unexplained phenomena, such as gamma-ray bursts, some of the universe's most energetic and mysterious outbursts. Human curiosity about the end of the universe has always been intertwined with our growing understanding of physics. Two powerful frameworks guide our predictions: general relativity and quantum mechanics. General relativity, developed by Albert Einstein, describes gravity and the motion of stars, galaxies, and the universe itself. Quantum mechanics governs the strange, probabilistic behavior of the tiniest particles. Together, they paint dramatically different pictures of the universe's final chapter. General relativity envisions the cosmos on a grand scale. Massive objects curve space and time, dictating how galaxies and stars move. It predicts that the universe's expansion could either reverse, leading to a collapse known as the Big Crunch, or continue indefinitely, fading toward a state of maximum entropy, a heat death where no usable energy remains. Observations reveal that the universe's expansion is accelerating, propelled by a mysterious force called dark energy. In this scenario, the universe could face a big rip, where galaxies, stars, planets, and even atoms are torn apart as expansion accelerates. Quantum mechanics, on the other hand, introduces randomness at the smallest scales. It suggests that even empty space is alive with fluctuations, where sudden events might spark entirely new universes or radically alter reality. The interplay between these two theories, the cosmic curvature of general relativity and the probabilistic quantum world, defines the edge of our understanding. The universe, vast beyond comprehension, is a stage for events both violent and awe-inspiring. From the quiet evaporation of the last black holes to the spectacular collisions of merging giants, it continues to evolve in ways that challenge human imagination. And though the ultimate fate of all things remains uncertain, each ripple, each collision, and each flicker of gravitational energy tells the story of a cosmos in motion. A story that stretches from the birth of stars to the quiet, dark eternity that may lie beyond. However, as we venture ever closer to realms of unimaginable density and searing temperatures, conditions that arise near black holes or during the universe's earliest moments, the elegant predictions of general relativity begin to falter. This theory, which has served as a remarkably reliable guide to the cosmic ballet of stars and galaxies, falters when confronted with the microscopic chaos of quantum uncertainty. At these extreme scales, the smooth curvature of space-time that Einstein described no longer provides the full picture. Tiny fluctuations, the jittery, ephemeral disturbances that permeate all of nature, become impossible to ignore. Because of this limitation, general relativity can outline broad scenarios for the ultimate fate of the cosmos, whether it be the slow, cold drift toward heat death, the violent implosion of a big crunch, or the rending of space itself in a big rip, yet it leaves profound mysteries unresolved. What truly occurs in those final infinitesimal instants when density approaches infinity? Can the very laws of physics as we understand them even retain meaning in such extremes? It is precisely here that quantum mechanics steps in, offering a radically different lens through which to perceive reality. Quantum mechanics governs the minuscule scales, where particles behave in ways that defy intuition. Unlike the predictable trajectories of macroscopic objects, quantum particles exist in states of probability, with their positions and motions described not with certainty, but with likelihoods. This core randomness is a defining feature of the quantum world, producing phenomena that clash with the smooth, deterministic predictions of relativity. Central to quantum mechanics is the principle of uncertainty, which declares that one cannot simultaneously know both the position and momentum of a particle with perfect precision. The more accurately one property is measured, the more elusive the other becomes. This intrinsic uncertainty transforms empty space itself into a restless sea, a dynamic arena of ceaseless fluctuations where particles and antiparticles spontaneously emerge and vanish. This churning microcosm, often called quantum foam, reveals a universe far more unpredictable and lively at small scales than classical physics could have imagined. When contemplating the ultimate fate of the cosmos, these quantum effects are not mere curiosities, they may be decisive. Consider the theoretical process of vacuum decay. A minute patch of space might undergo a sudden shift in its vacuum state, the lowest possible energy configuration of the quantum fields that suffuse the universe. Should such a shift occur, it could cascade outward, transforming the vacuum of the entire universe and rendering it inhospitable to the structures and particles that define our reality. Though highly speculative, this scenario illustrates how quantum mechanics introduces entirely new possibilities for cosmic endings, ones absent in classical thinking. Quantum tunneling offers another window into a cosmos governed by chance. In everyday life, objects require sufficient energy to overcome barriers, like a ball that must be thrown high enough to clear a wall. Quantum particles, however, can sometimes bypass barriers without the requisite energy, tunneling through seemingly insurmountable obstacles. Over vast spans of time, even a stable system could spontaneously alter its state, producing sudden and unpredictable transformations. Some theories that attempt to reconcile quantum mechanics with general relativity envision a universe that avoids catastrophic singularities entirely. Rather than ending in a catastrophic collapse or a violent tear, the universe might undergo a quantum bounce. In this vision, as the cosmos contracts to near infinitesimal size, quantum effects could halt the collapse and initiate a new phase of expansion, ushering in an endless cycle of cosmic renewal. Such a cyclic universe suggests that the apparent end of one cosmic epoch is merely the prologue to another, a concept both profoundly different and unexpectedly hopeful compared to the stark finality implied by classical physics. Quantum mechanics challenges our fundamental notions of space and time. At the smallest scales, space-time may not be continuous and smooth, but discrete, comprised of tiny, indivisible units. Some approaches to quantum gravity, efforts to fuse the principles of general relativity and quantum mechanics, propose that the fabric of the universe itself is granular. If true, the infinite densities predicted by classical singularities could be avoided, replaced instead by a more nuanced, finite structure. This revelation would profoundly alter our understanding of cosmic destiny. Rather than a sudden, catastrophic finale, the universe might transition into new states in ways our current language and intuition struggle to capture. The contrast between general relativity and quantum mechanics reflects a clash of perspectives. The former describes the grand architecture of stars, galaxies, and spacetime, dominated by gravity's steady hand, while the latter delves into the microscopic theater of particles, energy, and chance. Relativity offers a universe of sweeping, continuous motions, where cosmic fate is governed by the interplay of gravity and dark energy, predicting either eternal expansion, dramatic contraction, or ultimate disintegration. Quantum mechanics, by contrast, paints a jittery, unpredictable universe at small scales where fluctuations can trigger abrupt and radical changes beyond the reach of classical equations. The true challenge arises where these two domains intersect, at extreme densities and conditions where both are indispensable. In a hypothetical Big Crunch, for instance, relativity predicts a singularity, a point of infinite density and zero volume where known physics collapses. Quantum mechanics suggests an alternative. The singularity might be smoothed over by fundamental uncertainties, quantum fluctuations, or granular spacetime, preventing total collapse and hinting at a more intricate, perhaps less catastrophic ending. In this interplay of the vast and the minute, the smooth and the uncertain, modern physics invites us to reconsider not just how the universe ends, but what it truly means for anything to end at all. The cosmos, it seems, may be both stranger and more resilient than classical intuition allows, revealing a dynamic, ever-evolving reality that stretches our imagination and challenges our deepest assumptions about the nature of existence. However, quantum mechanics suggests that at the tiniest scales, where energy densities soar to unimaginable extremes, the smooth, continuous fabric of spacetime may unravel into a tumultuous sea of fluctuations. In this chaotic realm, the concept of a singularity, a point of infinite density and curvature predicted by classical physics, may never truly materialize. This is not merely an abstract theoretical puzzle. It highlights a profound and unresolved tension at the heart of modern physics. For decades, scientists have sought to construct a theory of quantum gravity, a framework that would reconcile the elegant continuous geometry of general relativity with the jittery, probabilistic nature of the quantum world. Such a theory holds the promise of revealing with unprecedented clarity the ultimate fate of the universe, from its fiery beginnings in the Big Bang to whatever lies beyond the final frontier of cosmic evolution. Until such a theory is realized, we are left to navigate a universe with two conflicting narratives, one smooth, elegant, and predictable, the other unpredictable, chaotic, and full of astonishing surprises. The divergence between these two frameworks becomes especially pronounced when we examine the very nature of time itself. In the classical framework of general relativity, time is treated as a dimension, much like the three spatial dimensions, flowing inexorably forward, intimately linked with the curvature of space. Under this lens, the end of the universe might appear as a singular moment, a halt in the passage of time, or as a gradual, endless stretching, a slow fading expansion toward a frigid, dark state. Quantum mechanics, however, complicates this picture. Some interpretations suggest that time may not be a fundamental backdrop at all. It might instead emerge from deeper, timeless processes at the quantum level. If time is dynamic, flexible, and context-dependent, then the universe's end might not be a single, easily identifiable event, but a complex, gradual transition, one that defies our conventional notions of beginnings and endings. The contrast between general relativity and quantum mechanics becomes most striking under extreme conditions, driving the quest for a unified theory capable of reconciling both perspectives. Two leading contenders in this search are loop quantum gravity and string theory. Loop quantum gravity proposes that spacetime is not a smooth continuum, but a lattice of discrete loops, forming a kind of quantum fabric. In this framework, the catastrophic singularities predicted by general relativity could be replaced by a quantum bounce, a transition that allows a contracting universe to expand anew, potentially establishing a cyclic pattern of cosmic evolution. String theory, in contrast, posits that the fundamental constituents of reality are not point-like particles, but infinitesimally small, vibrating strings. The vibrations of these strings determine the nature of particles, and the theory itself aims to unify all fundamental forces, including gravity, within a single, elegant framework. String theory also opens the door to revolutionary ideas about the universe's end. In some models, the vacuum of space is not fixed but capable of quantum fluctuations that might generate entirely new universes, a process evocatively described as cosmic rebirth. Despite their promise, neither approach has yet produced a complete theory of quantum gravity. The mathematics involved is dauntingly complex, and many predictions remain speculative. Yet the pursuit itself represents one of the most thrilling frontiers of science. A fully realized theory of quantum gravity would not only reconcile the apparent contradictions between general relativity and quantum mechanics, but also provide a profound understanding of the cosmos, from the explosive origin in the Big Bang to the ultimate fate of all that exists. Given the strikingly different predictions of these two pillars of physics, what might the end of the universe actually look like? General relativity offers scenarios such as eternal expansion, in which galaxies drift apart and stars burn out until the cosmos becomes a cold, dark void, a state referred to as the heat death. In this drawn-out ending, energy becomes so diffuse that work can be performed, and the universe slowly approaches absolute zero, fading into inert silence. Another dramatic scenario emerging from general relativity is the Big Rip. If dark energy continues to accelerate cosmic expansion, it could eventually become so overwhelming that it tears apart galaxies, solar systems, planets, and even atoms themselves, disassembling the very fabric of space. This violent finale contrasts sharply with the slow, inevitable fade of heat death. Quantum mechanics introduces entirely different possibilities. One of the most tantalizing is the quantum bounce, in which a contracting universe avoids catastrophic collapse thanks to quantum effects, reversing its contraction into a new expansion. This suggests a cyclic cosmos, a cosmic phoenix eternally rising from its own ashes. Another possibility, vacuum decay, exploits the inherent randomness of quantum mechanics. In this scenario, the vacuum of space, the state of lowest possible energy, may be unstable. Quantum fluctuations could trigger a shift in the vacuum state in a small region, which then propagates, altering the fundamental constants of physics and reshaping the universe in a way hostile to all familiar forms of matter and life. The clash between general relativity and quantum mechanics regarding the end of the universe underscores a central dilemma in modern science. Each theory works brilliantly within its domain, yet they produce fundamentally conflicting predictions at extreme scales. This ongoing tension has spurred generations of physicists to seek a unified theory, one that could elegantly explain the cosmos across every scale. The search for quantum gravity is a journey into the unknown, aiming to illuminate how the universe operates simultaneously at its vastest and most minuscule dimensions. Whether through loop quantum gravity, string theory, or a yet undiscovered framework, the goal is to trace the cosmic story from the Big Bang to the final frontier. Beyond the technicalities, these differing predictions carry profound philosophical implications. They challenge our assumptions about the nature of endings, permanence, and transformation. The universe might not end with a bang or a whimper, but could instead cycle endlessly, rebound quantum mechanically, or even experience radical vacuum transitions that redefine reality itself. These possibilities confront us with questions about time, space, and existence that stretch the imagination and defy everyday intuition. Ultimately, the stories offered by general relativity and quantum mechanics force us to rethink what it means for the universe to end. General relativity envisions endings shaped by the balance of gravity, matter, and dark energy. A collapse, a gradual fade, or a cosmic tearing apart. Quantum mechanics, with its unpredictable fluctuations and probabilistic nature, opens a door to scenarios of rebirth, fundamental transformations, and astonishing possibilities where the cosmos might never truly cease to exist. The end of the universe, it seems, is not a single inevitable event, but a canvas of possibilities, a profound mystery that challenges our understanding of reality itself. The quest for a unified theory of quantum gravity remains one of the most ambitious and exhilarating pursuits in modern science, holding the potential to finally illuminate the ultimate fate of the cosmos. It is a journey that reaches far beyond the boundaries of everyday experience, seeking to weave together the seamless, elegant fabric of general relativity with the untamed, unpredictable tempest of quantum mechanics. As physicists delve into the challenge of merging these two grand frameworks, they are not merely attempting to chart the ultimate fate of the cosmos. They are striving to uncover the very foundation of reality itself, to illuminate the principles that govern every atom, every star, and every galaxy. Meanwhile, the contrast between the smooth, deterministic vision of the universe and the restless, probabilistic dance dictated by quantum phenomena continues to spark debate, awe, and boundless curiosity. Whether the universe is destined to end in a spectacular collapse, a gradual fading into cold darkness, or a sudden, transformative shift that resets existence, the narrative of its ultimate fate mirrors the profound mysteries at the heart of nature. One might suggest that the cosmos does not adhere to the simplicity of a single conclusion. Rather, its ending may be as intricate, layered, and enigmatic as the story of its birth. Perhaps the final chapter is not truly an ending, but a momentary pause before an entirely new cycle begins. Concepts like a cyclic universe, a quantum bounce, or the emergence of multiple universes from vacuum decay hint that the end of our own universe could be a doorway to realms entirely beyond human imagination, a cosmic rebirth that challenges conventional notions of beginnings and endings. Within this framework, the tension between general relativity and quantum mechanics ceases to be a problem demanding a solution. It becomes a fertile ground for new ideas, a wellspring from which the frontiers of science are continually pushed. Our understanding of the cosmos is not static, and the enigmas of the universe serve to inspire both scientists and philosophers alike. As we peer into the future, the interplay between these two monumental theories promises discoveries that could redefine our perception of reality once more. Whether the cosmos concludes through the slow, inevitable cooling of a heat death, the violent unraveling of a big rip, or the hopeful rebirth promised by a quantum bounce, the ultimate destiny of existence remains among the most compelling and profound inquiries in science. At scales smaller than atoms, space itself is far from empty. It is a roiling, restless ocean, teeming with quantum fluctuations. These ephemeral and spontaneous energy shifts ripple through every corner of the vacuum, appearing even where, by classical standards, nothing should exist. Picture a pot of water brought to a boil. The surface never rests, continuously bubbling, forming and collapsing tiny pockets of motion. In a similar fashion, the void of space bubbles with energy as quantum fluctuations cause particles and antiparticles to spring into existence only to vanish almost instantaneously. Though these processes unfold on unimaginably tiny scales, they are essential to the universe's operation. Quantum fluctuations are more than theoretical constructs. They have been observed, tested, and measured. The Casimir effect, for example, reveals that even a vacuum is imbued with activity, as virtual particles exert measurable forces between objects. This leads to a tantalizing question. If quantum fluctuations can create particles, might they also give rise to entire universes? The theory of cosmic inflation offers a clue. In the moments following the Big Bang, the universe expanded at a speed that defies ordinary comprehension, growing exponentially from a minuscule origin. Some scientists suggest that if a quantum fluctuation were to replicate such an explosive expansion, it could birth a wholly new, self-contained universe. Imagine inflating a balloon. As air rushes in, the balloon stretches rapidly, becoming far larger than its original size. Now imagine this principle applied not to rubber, but to space itself. A quantum fluctuation forming a tiny, dense point under ideal conditions could expand dramatically, producing a universe separate from our own. This is the foundation of the inflationary multiverse hypothesis, a vision where our universe is only one among countless others, each arising from different quantum fluctuations in an infinite cosmic sea. These universes may obey different physical laws, contain different particles, or even possess alternative dimensions of space and time. Many researchers propose that our own cosmos may have originated as a quantum fluctuation within some larger, hidden reality. Prior to the Big Bang, the familiar concepts of space and time may not have existed. Instead, there may have been only a quantum void, a chaotic expanse filled with random energy fluctuations. From one of these fluctuations, a runaway expansion could have been triggered, the very event we now call the Big Bang. That infinitesimal spark eventually unfolded into all matter, galaxies, stars, and planets. This model aligns with certain interpretations of quantum mechanics and inflationary cosmology, implying that universes can emerge from what appears to be nothingness. If this is so, it invites even more staggering questions. Could quantum fluctuations give birth to new universes in the future? Might they account for the precise laws of physics governing our reality? Are universes continuously forming and vanishing beyond our observational reach? Quantum tunneling adds another layer of wonder. Here, particles bypass barriers that classical physics deems insurmountable. Imagine a ball resting at the bottom of a hill. Ordinarily, it would require enough energy to roll over the peak. Yet, in the quantum world, the ball can sometimes tunnel through the hill, appearing on the other side as if by magic. Some scientists speculate that quantum tunneling could facilitate the creation of new universes. If a sufficiently dense energy fluctuation arises, tunneling might allow it to inflate into a fully realized cosmos. This concept underpins the false vacuum hypothesis, suggesting our universe occupies a temporary, unstable state. Should it transition to a lower energy configuration, it could either spark a completely new universe or radically alter the existing one. Black holes, too, may harbor secrets of cosmic creation. These regions of space, where gravity is so intense that not even light can escape, conceal singularities of infinite density where conventional physics collapses. Certain physicists propose that matter falling into black holes might be compressed and repackaged into nascent universes. In this view, each black hole could conceal the seed of a separate cosmos, entirely isolated from our own. If this holds true, then our universe itself might reside within a black hole formed inside a greater universe, rendering black holes not just destructive phenomena, but potential wombs of new realities. From the dawn of human curiosity, people have pondered the origins of existence. Across millennia, from myth to mathematics, humanity has sought to understand how everything came into being. Scientific advances, particularly in physics, have radically reshaped these notions. Once, the belief was singular. There is only one universe, finite and comprehensible. Today, the tapestry of possibility is far broader, woven from the interlacing threads of quantum mechanics, relativity, cosmic inflation, and multiverse theory, inviting us to reimagine the universe as a dynamic, ever-expanding ensemble of realities, each filled with its own mysteries, waiting to be discovered. But now, a growing number of scientists are seriously considering a possibility that stretches the imagination. There may be not just one universe, but countless universes, perhaps even an infinite number of them. This mind-bending concept has been given a name: the multiverse. Among the most captivating aspects of this idea is the notion of bubble universes, entire realities forming like soap bubbles drifting in a vast cosmic sea. At the heart of this vision lies the bubble universe theory. Picture each universe as a fragile, iridescent bubble floating in an endless ocean of space. Some bubbles are enormous, others minuscule, and new ones are constantly forming, emerging from regions of space where conditions trigger a spectacular birth. Our own universe is merely one among these countless bubbles, existing alongside others with an astonishing variety of possibilities. Some may resemble our familiar cosmos, with galaxies, stars, and planets, while others could be unrecognizably different, governed by bizarre physics where gravity is intense, light behaves strangely, or time itself runs backward. The origins of this idea are rooted in a deeper understanding of cosmic inflation, a groundbreaking theory in physics. Introduced by physicist Alan Guth in the 1980s, cosmological inflation was devised to solve some of the greatest mysteries of the universe's earliest moments. Scientists had realized that the universe must have expanded at an incredible pace immediately after the Big Bang. This super-fast growth, called inflation, explains why the cosmos appears remarkably smooth and uniform, with galaxies evenly spread rather than clustered in chaotic patches. Yet, while inflation was originally thought to be a brief, almost instantaneous event, some physicists pushed the idea further, leading to the concept of eternal inflation. Unlike standard inflation, eternal inflation proposes that the process never completely stops. Instead, certain regions of space continue to expand at unimaginable speeds, while others, like the space we inhabit, settle down to form stars, galaxies, and planets. The inflating regions eventually pinch off, forming new bubbles, each one a universe unto itself, following its own path and laws. Imagine the cosmos as a vast pot of boiling water, each bubble that rises representing a distinct universe springing into existence. The formation of each bubble universe occurs when inflation slows in a specific region of space, often triggered by a quantum process called quantum tunneling. This can be visualized as a ball perched on top of a hill. Ordinarily, it would roll down to reach the bottom, but in the strange world of quantum mechanics, the ball can instead teleport to the bottom. In the same way, a patch of inflating space can suddenly drop in energy, creating a hot, dense environment, the birth of a new universe. Inside this bubble, time and physics unfold independently, perhaps mirroring our own universe or diverging wildly. Each bubble begins with its own version of a Big Bang, expanding and evolving in isolation from its siblings. The multiverse, if real, opens an unimaginable spectrum of possibilities. Some universes could closely resemble ours, complete with familiar galaxies and planets, even bearing near-identical copies of Earth. With infinite variations, there could be countless versions of ourselves, each living different lives in parallel realities. Other universes might defy everything we understand, operating under alternate physical laws where atoms never form, gravity is a foreign concept, or stars and planets never coalesce. Some could exist as barren voids, while others may be composed of exotic forms of matter and energy beyond our comprehension. In certain universes, time itself might flow backward, where the future is fixed and the past yet to unfold, a world where people grow younger instead of older. Some theorists even propose universes that exist purely as mathematical structures with no tangible matter, only patterns of energy or information, hinting that reality itself could be fundamentally mathematical. Science fiction often portrays interuniversal travel, but reality remains far more daunting. Each bubble universe is separated by an invisible boundary that prevents interaction. Even approaching the edge would be catastrophic, as the physics we rely on may break down entirely in another universe, akin to a fish suddenly encountering the vacuum of space. Some speculate that wormholes, hypothetical shortcuts through the fabric of space and time, could provide a bridge between universes. If such phenomena exist and could be harnessed, travel between universes might someday move from fiction toward possibility. Yet, despite the fascination and speculation, the multiverse remains a theory. Unlike stars, galaxies, or black holes, other universes are beyond our current observational reach. Their existence challenges the very limits of human comprehension, pushing the boundaries of physics, imagination, and philosophy. Each bubble might be teeming with life, utterly alien or entirely inert. Each one is a reminder that the cosmos may be far grander and stranger than we have ever dared to imagine, an endless ocean of universes bubbling silently in the depths of infinity. However, there are subtle hints scattered throughout the cosmos that suggest possibilities far beyond our everyday understanding, whispers from the universe that hint at something far larger and stranger than the one we inhabit. For instance, some astrophysicists and cosmologists have proposed that unusual patterns in cosmic background radiation, the faint, pervasive afterglow left over from the Big Bang itself, might not just be random noise. They speculate these anomalies could be the remnants of a past collision between our universe and another bubble universe, a cosmic neighbor whose existence we can only infer indirectly. At the same time, other researchers look at the puzzling behaviors revealed in quantum mechanics experiments, where particles exist in multiple states until observed, and suggest that our reality may be just one thread in an enormous tapestry of possibilities. Until we acquire concrete, indisputable proof, the idea of the multiverse remains one of the most profound and tantalizing scientific mysteries humanity has ever encountered. You might ask, why should we devote attention to universes that may forever lie beyond our reach? The answer is intertwined with humanity's insatiable curiosity and our relentless quest to understand the nature of reality itself. If a multiverse exists, the implications are staggering. Our universe, with all its vast galaxies, stars, and planets, would be just one among an incomprehensible number of universes, each with its own unique properties and possibilities. This idea shatters centuries of assumptions about our cosmic significance. It opens the door to questions both philosophical and scientific. If there are infinitely many universes, are there also infinite versions of ourselves, each following different paths and choices? Could some of these universes contain lives and worlds unrecognizable to us, operating under laws of physics entirely alien to our experience? Pursuing these questions expands the boundaries of human thought, pushing us to envision realities far beyond what we can see. If the universe itself is part of a grand cycle, it may not only end once, but continue endlessly through what some theorists call the cyclic universe. In this model, the cosmos undergoes an eternal series of expansions and collapses, a cosmic rhythm akin to a phoenix perpetually rising from its ashes. Imagine the universe collapsing into a single, incomprehensibly dense point. Within that infinitesimal moment, the pressure and temperature could trigger a new, explosive expansion, a rebirth, a second, or perhaps a third Big Bang. Some scientists propose that this cosmic cycle has occurred countless times, making our universe merely the latest in an endless chain. Observations of cosmic background radiation have revealed anomalies that hint at the possibility of these prior universes leaving behind faint traces, though no definitive evidence has yet been found. Quantum mechanics adds another layer of speculation. At the smallest scales, particles behave in ways that defy classical intuition. Some theories suggest that as the universe compresses to near nothingness, quantum forces could exert an outward push, reigniting creation and giving birth to a completely new cosmos. That new universe could be unrecognizable to us, with laws of physics, dimensions of time and space, or forms of matter entirely alien. Alternatively, it might resemble our current universe, with galaxies, stars, and perhaps even life, shaped by the remnants of what came before. Such possibilities raise profound questions about continuity, memory, and survival on a cosmic scale. Consider the immense consequences. If a new Big Bang occurs, everything we know, the Milky Way, Earth, humanity itself, would be obliterated. Yet this process unfolds over timescales of billions or even trillions of years, far exceeding the lifespan of any human civilization. Some speculate whether future advanced civilizations could find a way to escape the demise of our universe, transferring existence into a nascent cosmos. Though purely conjectural, such ideas stretch the imagination and challenge our understanding of life, survival, and cosmic destiny. Picture a universe that has reached its ultimate death. Stars have extinguished, galaxies have drifted into irretrievable isolation, and even the smallest particles have decayed to nothingness. Time itself, the inexorable flow we take for granted, comes into question. Does it continue when all change has ceased, or does it end alongside the cosmos? Time is a concept we experience constantly, yet its essence eludes simple definition. It is the continuous flow from past to future, intimately intertwined with space in what scientists call space-time. Albert Einstein revolutionized this understanding, revealing that time is flexible. It stretches, compresses, and can slow down depending on speed and gravity. Yet time is inseparable from motion, energy, and transformation. We measure it through the rotation of the Earth, the ticking of a clock, or the burning of a star. If the universe were to reach a state of absolute stasis, what would become of time? To answer that, we must consider the story of the universe itself. Approximately 13,800 million years ago, the cosmos sprang into existence in the event we call the Big Bang, an explosion of energy that brought space, time, and matter into being. Since then, galaxies have formed, stars have ignited and died, and planets like Earth have emerged. Stars burn their fuel, explode as supernovae, and seed the cosmos with elements necessary for new stars, planets, and life. But this cosmic cycle will not persist forever. Eventually, the universe may exhaust its energy. Scientists predict several potential endpoints. The most widely discussed is the heat death, or Big Freeze, in which the universe expands eternally, stars burn out, galaxies drift apart, and even the faintest light dims to nothing. All motion ceases, leaving a cold, dark, and lifeless cosmos. Alternatively, the universe might collapse in on itself in a big crunch, reversing expansion and concentrating all matter and energy into a single point, potentially sparking another Big Bang. In either scenario, the fate of time becomes uncertain. If time is a measure of change, what happens when change itself disappears? Can the flow of past, present, and future persist when all movement halts? To grapple with this question, we must confront the very nature of measurement, of motion, and of existence in a universe poised on the brink of eternity. Today, we mark the passage of time by observing movement, by the rhythm of ticking clocks, the orbit of the Earth around the Sun, and the restless activity of particles at scales invisible to the naked eye. But imagine a universe stripped of all motion, no clocks, no planets, no particles vibrating with energy. Would time still exist in such a place? Some scientists contend that it would, but stripped of context, it would lose all meaning. Picture yourself in a vast, pitch-dark room, utterly silent, utterly still. Without any observable change, how would you know whether a second, a minute, or an hour had slipped by? Without difference, time becomes a hollow concept, devoid of purpose or reference. Others take the idea further, suggesting that time itself might eventually cease to exist. Some theoretical models propose that time is not a fixed entity, but an emergent property arising from the activity within the universe. If the cosmos were to fall into absolute stillness, time might simply dissolve, leaving existence in a state beyond chronology. Yet, even as the universe drifts towards such a profound stasis, one last remnant of cosmic vitality could persist for an almost unimaginable duration. Black holes. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape. They are the remnants of massive stars that have collapsed, devouring matter and energy from their surroundings. Even after all the stars have died, black holes endure, silent sentinels in a gradually darkening universe. However, even black holes are not eternal. Over periods so vast they boggle the human mind, periods on the order of 1 followed by 100 zeros, sometimes referred to as a Google years, they gradually lose mass through a subtle process known as Hawking radiation. Eventually, every black hole, no matter how massive, will evaporate, leaving only a thin mist of subatomic particles scattered across a cold, empty void. This is the final phase of cosmic existence, what scientists call the dark era. A universe in this state is utterly silent and still, devoid of stars, devoid of light, devoid of motion. The energy that once animated galaxies and powered stellar furnaces is stretched thin across an infinite emptiness. Yet, could time somehow begin anew? Some theoretical frameworks suggest that even in absolute emptiness, quantum events might still occur. Quantum mechanics, the science of the very small, shows that particles can spontaneously appear and disappear in ways that defy classical logic. Some physicists speculate that given infinite time, a random fluctuation in quantum energy could spark a new Big Bang, igniting a fresh universe from the void. This would imply an endless cycle of cosmic births and deaths, where universes emerge, flourish for billions or trillions of years, then fade into silence before a new one rises. In such a vision, time never truly ends, it merely resets over and over. Our human experience of time, however, is intimate and deeply personal. We measure our lives in seconds, minutes, hours, days, and years. We perceive time as a relentless forward motion, a current that never reverses. The notion that time could stop or even restart challenges everything we understand about reality. Consider the thought experiment of observing a dead universe. Would it feel like an endless frozen moment? Would the absence of change render time imperceptible, or would some underlying rhythm persist unseen? From birth, our perception of time is inseparable from the changes surrounding us. The sun rises and sets. Infants grow into children, then adolescents, then adults. Leaves shift through the spectrum of seasons, from green to gold to brown, before descending to the earth. Our brains are hardwired to detect patterns, cycles, and differences. This is how we know that time is passing. Imagine waking one day to a world in which nothing changes. The clock is frozen at the same hour, minute, and second. People do not move. The air is perfectly still. Hunger and fatigue are absent. Days do not turn into nights because the sun refuses to traverse the sky. Would time feel real in such a scenario? With no change to measure, even if consciousness remained, it would seem as though time itself had stopped. This underscores a profound truth. Time, at least in the way humans experience it, is inseparable from change. For centuries, scientists have debated whether time is a fundamental reality or merely a construct of human perception. Albert Einstein, whose theory of relativity revolutionized physics in the early 20th century, demonstrated that time is not absolute. It is flexible, influenced by speed and gravity. Astronauts orbiting Earth aboard the International Space Station experience time differently than those on the planet's surface. Moving at high velocities in a strong gravitational field, they age slightly less than their friends on Earth, a subtle but real distortion of temporal experience. But what if movement ceased entirely? If the universe became perfectly still, with no vibrating particles, no light traversing space, and no forces interacting, what would become of time? Some scientists argue that without change, time would lose all meaning, collapsing into an abstract concept without practical relevance. Moments could no longer be compared, measured, or marked. Others propose that time is an independent fabric of reality, persisting even in the absence of activity. In this view, time is fundamental, a background dimension woven into the structure of the cosmos, waiting silently even when no events occur to measure it. In such considerations, time transforms from a familiar, everyday metric into a profound cosmic mystery. It is at once intimately human and inescapably universal, tied to our perception yet potentially indifferent to it. The universe, whether teeming with activity or plunged into eternal stillness, challenges our understanding of what time truly is. It is the dance of change, the rhythm of stars and particles, and the silent passage of moments that define our reality. And even in the darkness of a silent, empty cosmos, the question lingers. Does time exist if there is nothing left to move, nothing left to change, nothing left to remember? Another captivating notion is that time might not simply halt, but instead could loop endlessly. Some scientists and philosophers have speculated that rather than moving along a linear path from the past to the future, time could form a vast circular pattern. In such a scenario, history would not march forward infinitely, but might instead repeat itself over and over again. Imagine the universe undergoing massive cycles of expansion and contraction. It grows for billions of years, then collapses back into a minuscule point, only to erupt outward once more in another colossal Big Bang. Within such cycles, every event could recur precisely as it did before. You could be reading this very sentence in an alternate version of reality countless times, trapped within an infinite loop. Every moment that has ever occurred could happen again, identical and indistinguishable from its prior iteration, while no observer would recognize the repetition. Would time retain its significance if the future were merely a reflection of the past, repeating perpetually? Some theories propose that even in an eternal loop, minute variations might emerge. Tiny differences could arise with each repetition, ensuring that no two versions of reality are perfectly identical. If this is true, then time would still matter, for change, however subtle, would continue to exist. Beyond the confines of science, philosophers have long pondered whether time is an objective reality or merely a construct of human consciousness. If no sentient beings were present to witness time, would it persist? Some argue that time is simply a framework humans use to comprehend existence. If nothing evolves and no consciousness perceives it, does time hold any meaning at all? Picture a cavern so deep and silent that no movement occurs, no sound reverberates, and no life stirs. If a clock were placed there, would time advance? Scientifically, the answer is yes, because the universe beyond the cave continues its transformations. Yet, if all existence were like that cave, frozen, quiet, unchanging, some philosophers contend that time itself might dissolve. Others maintain that time is an independent force inseparable from the universe, existing even without observation or measurement. In such a reality, even a completely static world would still possess the passage of time, invisible but undeniable. Life as we understand it hinges upon change, motion, and transformation. The Earth revolves around the sun, producing days, nights, and the shifting of seasons. Our bodies rely on countless microscopic hearts beat, cells regenerate, thoughts arise, and shift. Without change, these processes would cease and reality itself would become unrecognizable. If time lost its meaning, what implications would that hold for consciousness? Could awareness persist in a timeless state, or would existence resemble deep sleep or death, a state devoid of perception where time has no relevance? Conversely, if time is merely a human invention, its disappearance would leave the universe intact, but stripped of past, present, or future. Grasping this is challenging because every facet of human experience is anchored in the flow of time. The simulation hypothesis expands this contemplation to an even more radical level. It suggests that all we see, feel, and experience might not be genuine reality, but part of an intricate, hyper-advanced simulation, a colossal computational construct in which we exist merely as digital entities. In 2003, philosopher Nick Bostenram articulated what he called the simulation argument. He proposed that if a civilization advanced enough to create conscious beings within a simulation exists, it would likely produce vast numbers of such beings. Under this premise, the probability that any one conscious entity, like you or me, resides in the real world would be extraordinarily low. Instead, we would almost certainly inhabit a simulated reality. Bostenram framed his argument as a trilemma, outlining three potential outcomes. 1. Advanced civilizations never reach a level capable of creating simulations, either because they self-destruct beforehand or the technology proves unattainable. 2. Advanced civilizations choose not to create simulations, perhaps due to ethical concerns or a lack of interest. 3. If simulations are created, the number of simulated beings vastly outnumbers real ones, making it overwhelmingly likely that we exist within a simulation. This theory assumes that consciousness is not restricted to biological brains. Any sufficiently sophisticated computational system could theoretically think, feel, and perceive as humans do. While the notion of a simulated world may appear futuristic, the question of reality versus illusion has intrigued thinkers for millennia. Ancient philosophies often questioned whether the world is what it seems. The Chinese philosopher Zhuangzi famously dreamt he was a butterfly, later wondering if he were a butterfly dreaming he was a man. In Indian philosophy, Maya represents the world as an illusion that conceals a deeper truth. Ancient Greek philosophers likened reality to a painted scene or dream, suggesting our perceptions may not reflect ultimate reality. The Aztecs envisioned the world as a book or painting authored by the divine force Teotl. Plato's allegory of the cave, written in the 4th century BCE, depicts individuals chained in darkness, perceiving only shadows on a wall and mistaking them for reality, while a greater world exists beyond their sight. In the 17th century, philosopher René Descartes proposed a radical thought experiment. An evil demon might manipulate all perceptions, rendering everything experienced as illusion. This idea evolved into the brain in a vat scenario, where a brain linked to a supercomputer experiences an entirely artificial reality without awareness of its artificiality. In the 20th century, scientific inquiry joined the philosophical debate. In 1969, German scientist Konrad Zuse proposed in his book Calculating Space that the universe might function as a vast computational system, a notion that later contributed to digital physics. Boston Ram's trilemma does not assert definitively that we inhabit a simulation. Instead, it contends that one of 3 possibilities must hold true. Few civilizations ever reach extreme technological advancement. Advanced civilizations refrain from creating ancestor simulations, or if simulations exist, most conscious entities in the universe are simulated. If the 3rd scenario is correct, nearly every conscious being, including ourselves, would dwell within a simulated world rather than a physical reality. Boston Ram argues that, given the technological capabilities of future civilizations and absent ethical restrictions, it is exceedingly improbable that we are among the few real beings. Rather, we are likely part of a vast population of simulated consciousnesses. The question then arises, if we live in a simulation, how could we detect it? Some scientists have proposed tests to identify anomalies, glitches, or patterns hinting at the underlying code of our existence. Though speculative, the concept is not entirely beyond proof. Boston Ram envisions a scenario in which a message might suddenly appear on a screen declaring, "You are in a simulation." Click here for more information. Time looping endlessly, reality as illusion, consciousness as computation, these are not mere thought experiments. They represent profound inquiries into the very fabric of existence, challenging our understanding of what is real, what is fleeting, and what might be eternal. However, if reality itself were merely a simulation, its imperfections might be so subtle and deeply embedded that those living within it would never perceive them. Every glitch, every anomaly could be smoothed over by the system orchestrating the simulation, perhaps even erasing memories of any moment when the illusion threatened to falter. Yet, if incontrovertible evidence were ever discovered, proof that reality is either authentic or fabricated, the impact on humanity's understanding of existence would be seismic. The very probability of living within a simulated universe would shift, altering philosophy, science, and culture in ways we can scarcely imagine. Boston Ram pushes this contemplation beyond traditional skepticism, offering a framework rooted in scientific reasoning rather than abstract doubt. He proposes that, logically, one of 3 scenarios must hold true. First, human civilizations never advance to a point of extraordinary technological achievement because they inevitably self-destruct or are extinguished by external forces. Second, civilizations do reach such advanced stages, yet for reasons unknown, they refrain from creating realistic simulations of their ancestors. Third, civilizations do develop these simulations, and if this is the case, it follows that we are almost certainly already embedded within one of them. Boston Ram refrains from claiming knowledge of which scenario is accurate, noting that different observers are naturally inclined to favor different possibilities. Some accept the inevitability of human extinction, aligning with the first scenario. Others believe that advanced civilizations simply avoid running simulations, resonating with the second. And a third group contends that the evidence suggests our reality is itself a sophisticated simulation, the third scenario. From his perspective, if we are not currently inhabiting a simulation, then it is almost certain that future civilizations will never undertake the creation of ancestor simulations at all. This assertion has sparked debate, with some philosophers questioning whether simulated beings could possess genuine consciousness. If simulated humans are not truly self-aware, then Boston Ram's reasoning may lose much of its persuasive force. Alternative viewpoints suggest that humans might possess an intrinsic sense of their own reality, a natural awareness distinguishing authentic existence from artificial constructs. Philosopher Barry Dayton offers a refined iteration of Boston Ram's argument. He shifts the focus from broad ancestor simulations to high-fidelity neural simulations. These could manifest as brains in vats, where individual human brains are preserved artificially and supplied with precise sensory experiences, or as scenarios where future humans are convinced they are living as their distant ancestors. In such simulations designed with extreme precision, the inhabitants would be incapable of discerning the simulated from the real. Dayton concludes that if such simulations are possible, then one of two realities must be correct. Either almost no civilizations achieve the capability to run them, or we are already residing within one. Many scientists remain unconvinced by these ideas. Physicist Sabine Hosenfelder argues that generating a universe-wide simulation without introducing inconsistencies is physically impossible. She dismisses the concept as pseudoscience, comparable to religious faith. Cosmologist George Ellis concurs, stating that the theory is implausible from a technical standpoint and better suited for speculative conversation than rigorous scientific inquiry. Some skeptics suggest that the simulation could exist in its first iteration, meaning not all simulated beings destined to exist in the future have been instantiated yet. This view echoes philosophical presentism, the belief that only the present moment possesses true existence. Physicist Shaw Carroll highlights a logical contradiction within the simulation hypothesis. If most humans throughout history are simulated, yet humans themselves cannot run such simulations, the assumption that other civilizations have successfully built them becomes questionable. Similarly, physicist Frank Wilczek draws attention to the unnecessary complexities in physical laws, arguing that a simulation would not require such elaborate rules. He further asks, if our universe is simulated, what is the nature of the reality that contains the simulator? What laws govern that external system? Each answer seems to generate further questions, creating an endless loop of uncertainty. Brian Eggleston extends this line of critique, suggesting that future humans within our own universe could not be the architects of the simulation, as our universe itself is purportedly the one being emulated. Thus, the probability of residing in a simulation is intimately tied to the existence of other universes beyond our own. Some scholars contend that following Boston Ram's reasoning, one of the first two possibilities, human extinction before achieving simulation capability, or advanced civilizations choosing not to simulate, must be true. Physicist Paul Davies uses this argument to challenge the concept of a near-infinite multiverse, reasoning that if infinite universes existed, some would inevitably contain post-human civilizations conducting simulations. If this were the case, the notion that we are currently inside a simulation would become uncomfortably inescapable, undermining the plausibility of an infinite multiverse. Currently, there is no empirical evidence for technology capable of producing such high-fidelity simulations, nor do we know if the laws of physics would even allow a civilization to construct a perfect digital replica of a universe. Some scientists argue that until such proof emerges, we should assume the first scenario. Civilizations never reach the stage necessary to create authentic ancestor simulations. Furthermore, inherent limitations exist in computational capacity, suggesting that even the most advanced civilizations might lack the resources to simulate a universe in exhaustive detail. Physicist Marcelo Glaser challenges the assumption that posthumans would be motivated to run comprehensive simulations of entire universes. By the time civilizations reach such advanced intelligence, Glaser contends, they would already possess extensive knowledge of their history, reducing any incentive to simulate it fully. Instead, they might prefer curated virtual experiences, such as immersive historical museums, allowing them to witness and empathize with the lives of their ancestors without replicating the entire complexity of the past. In this framework, the question of whether we inhabit a simulated reality becomes not only a scientific puzzle, but a philosophical labyrinth, touching on consciousness, technological possibility, and the ultimate nature of existence itself. The theory forces us to confront unsettling possibilities, that our experiences, our memories, and even our sense of free will may be orchestrated by forces beyond our comprehension. It challenges the very foundation of what it means to be real, leaving humanity suspended between empirical uncertainty and speculative imagination. However, GLA regards the notion of conducting a full-scale, resource-draining simulation of an entire universe as an exercise in futility of monumental proportions, a task so vast and so consuming that its very attempt seems almost absurd. He emphasizes a crucial complication. If such simulations were possible, there is no reason to assume they would halt at a single layer. The beings within these simulations could, in turn, develop their own nested simulations, spiraling into an endless recursive loop reminiscent of the age-old philosophical conundrum of the first cause, which questions the ultimate origin of everything, probing the very inception of existence itself. In the year 2019, philosopher Preston Green introduced a provocative perspective. He suggested that if humanity exists within a simulation, it might be wiser to remain ignorant of the truth. Green expressed concern that proving the artificial nature of our reality could provoke the entities controlling the simulation to terminate it, abruptly erasing everything we know and experience. Meanwhile, economist Robin Hanson approached the dilemma from a different angle. He posited that if our reality is a high-quality simulation, it may be in our best interest to behave in ways that appeal to those orchestrating it. Failure to do so could result in being erased or relegated to a lower-quality simulation, a world with diminished awareness and weaker consciousness. Hansen even speculated that a firm belief in living within a simulation might fundamentally alter human motivation. The knowledge that one would never truly retire, or that specific locations, such as Ethiopia, exist only within the simulation, could diminish incentives to plan for the future or act altruistically. Beyond debating the literal truth of the simulation hypothesis, philosophers have harnessed the concept to explore deeper metaphysical and epistemological questions. Philosopher David Karras, for instance, proposed that simulated beings might question whether their thoughts and mental experiences are determined by the simulated universe's physical laws, when in fact their consciousness could operate independently of those constraints. If so, their thoughts would not be causally tied to the simulation's physics, challenging the long-standing belief that mind and body are inextricably linked, a view known as Cartesian dualism. Karras stops short of fully endorsing dualism, yet contends that it is far less problematic than commonly portrayed. Similar lines of inquiry extend to personal identity, questioning whether an individual could have existed as an entirely different person under alternate circumstances. Other debates explore the nature of perception, particularly color perception, suggesting that our experience of color could vary drastically if our cognitive processes were wired differently relative to the simulated world. Interwoven with these ideas is computationalism, a theory in the philosophy of mind which posits that thought is fundamentally a form of computation. This perspective holds particular relevance for the simulation hypothesis, as it implies that a simulated environment could harbor conscious entities, or virtual people. Given that physical systems can be accurately modeled computationally to some degree, computationalism argues that if consciousness can be artificially instantiated, a self-aware simulation is theoretically feasible. Yet this notion remains fiercely contested. Critics argue that consciousness may demand more than computation alone, invoking qualities beyond the reach of any algorithm. If true, human-like behavior within a simulation could be mere mimicry, producing what philosophers term philosophical zombies, beings that appear conscious but lack genuine awareness. Should consciousness resist computational replication, foundational arguments such as Nick Bostrom's famous simulation hypothesis lose traction. However, this does not eliminate the possibility that humans might still be brains in a vat, fully self-aware minds confined within an artificial environment. Some theorists extend the argument further. If consciousness truly is computational, and if mathematical realism, the belief that mathematical structures exist independently, is valid, then consciousness could arise on any computational substrate, including simulations. This suggests that awareness is not tethered to a particular physical form and could theoretically be instantiated anywhere a sufficient computational framework exists. Futurist Hans Moravich explored this concept extensively, proposing that even the simplest physical objects, such as a rock, might be performing every conceivable computation, implying that reality itself could already be an immense, complex mathematical simulation. These ideas compel profound reflection on existence, technological limits, and the nature of reality itself. Some physicists view the universe not merely as stars, planets, and galaxies, but as a vast dynamic information processor functioning akin to a colossal computational system. John Archibald Wheeler first articulated this notion, framing the universe as a mechanism deeply intertwined with information. Over time, two dominant perspectives emerged. One positing the universe itself as a quantum computer, continuously calculating and processing data, and the other suggesting that our universe might be a simulation, a programmed reality maintained by external agents or mechanisms beyond our perception. Quantum computing expert Dave Bacon adds nuance to this discussion, highlighting that in our contemporary era, where computation and information technology permeate every aspect of life, humans are inclined to interpret even the fundamental laws of physics through the lens of computation. In other words, the way we conceptualize reality may be shaped as much by our technological context as by the underlying structure of the universe itself, blending human cognition with the abstract possibilities of simulated existence. However, he also highlighted a critical dilemma. No one has ever uncovered definitive evidence proving that our universe functions like a digital system, in the same way computers process information. There are no unmistakable signs of discrete, indivisible units of information, akin to computer bits, that one would expect if reality were truly digital. Predictions put forward by proponents of this idea have, so far, failed to hold up under experimental scrutiny. In the year 2012, three physicists, Silas Bean, Zor Devoti, and Martin Savage, proposed a method to test one version of the simulation theory. Their approach was rooted in the notion that any simulated environment would inevitably face limitations, much like a computer program, which can only process so much data before slowing down or crashing. If our universe were indeed a simulation, the underlying program would have to discretize space and time into tiny separate points, rather than allowing for a perfectly smooth continuum. Such discretization could produce detectable anomalies. One possible manifestation of this, they suggested, might appear in cosmic rays, high-energy particles traveling through space. If these particles displayed an irregular or uneven distribution, it could serve as indirect evidence that we inhabit a simulated world. By 2017, another team of scientists, led by Tom Campbell, proposed additional experimental approaches aimed at testing the simulation hypothesis. They speculated that, with the right techniques, it might be possible to detect glitches or inconsistencies within our observed reality, hinting at the presence of a complex computational substrate beneath the universe itself. Prominent intellectuals and public figures have also weighed in on this debate. In a 2018 interview with NBC News, astrophysicist Neil deGrasse Tyson suggested that the probability of living in a simulation might be better than even. He acknowledged his difficulty in constructing a convincing argument against it. However, in a subsequent discussion with Princeton professor J. Richard Gott, Tyson encountered a thought-provoking counterpoint. Gott argued that if simulated universes can give rise to other simulations, we should expect to see such activity occurring around us. Since humanity has yet to develop the capacity to produce high-fidelity simulated universes, two possibilities remain. Either we inhabit the original base-level reality in which no simulations exist yet, or we are near the end of a long chain of nested simulations. The latter scenario seems highly improbable, leading Tyson to reassess the likelihood of the simulation hypothesis and ultimately view it with greater skepticism. Elon Musk, the entrepreneur behind Tesla and SpaceX, has been a vocal advocate of the simulation theory. In interviews and press events, he has argued that the progression of video game technology will inevitably lead to virtual environments indistinguishable from reality. In a 2016 interview, Musk estimated that the chance of living in base reality is 1 in a billion. He contended that it is almost certain we inhabit a computer-generated universe, crafted by a civilization far more technologically advanced than our own. Rizwan Virk, a researcher at the Massachusetts Institute of Technology and author on the subject of the simulation hypothesis, has shared personal experiences that shaped his perspective. He recounted a moment when using a virtual reality headset, he became so immersed that he momentarily forgot he was standing in an empty room. This experience led him to ponder, if a relatively simple device can obscure our sense of reality, could it be that our entire universe is a construct engineered by a far superior intelligence? The idea that reality may be an illusion is far from modern. Philosophers have wrestled with this question for millennia. Ancient Chinese thinker Zhuangzi famously told the story of the butterfly dream, in which he dreamt of being a butterfly, fluttering joyfully, only to awaken as Zhuangzi. He pondered whether he was a man dreaming of being a butterfly or a butterfly now dreaming of being a man. This philosophical puzzle mirrors the core of simulation theory. How can we be certain that our experiences reflect an underlying reality? Similar notions appear in Indian philosophy through the concept of Maya, which posits that the physical world is an illusion. Ancient Greek philosophers, including Anaxarchus and Monimus, likened life to a painting or dream, suggesting that sensory experience might not reflect true reality. In the 17th century, René Descartes famously questioned whether all perceptions might be false, arguing that the vivid realism of dreams makes it impossible to be completely certain we are not perpetually dreaming. Modern thinkers, such as David Chalmers, have extended these ideas with variations of the dream hypothesis. One version suggests we are dreaming at this very moment, and a more radical variant proposes that our entire history of experiences exists solely within imagination. Some philosophers, like Ludwig Wittgenstein, dismiss such extreme skepticism, asserting that foundational assumptions about reality are necessary for any meaningful discourse. Beyond philosophy, literature and mythology have explored similar concepts. The Aztecs envisioned the world as a painting or a book created by a divine entity called Teotl. Friedrich Nietzsche, in his work Beyond Good and Evil, challenged the notion of a singular hidden reality behind appearances, proposing that what we call truth may be nothing more than a human invention. For centuries, scientists have pursued the fundamental constituents of the universe. Once thought indivisible, atoms were revealed in the 20th century to contain protons, neutrons, and electrons. Electrons remain fundamental, indivisible particles, while protons and neutrons are composed of smaller entities called quarks, bound together by extraordinarily strong forces. Protons are generally considered stable, resistant to decay or fragmentation over time, underscoring the universe's intricate and resilient structure. However, some of the most cutting-edge theories in modern physics propose a startling possibility. Protons, the seemingly eternal building blocks of matter, might not be eternal after all. If this is true, the consequences would shake the very foundations of our understanding of the universe, challenging everything from the stability of matter to the ultimate fate of itself. But what does it mean for a proton to decay, and what would actually occur if this fundamental particle were to disintegrate? This question has fascinated physicists for decades, sparking intense research and intricate experiments designed to uncover the proton's ultimate fate. If protons do indeed break apart, the implications for the cosmos, for physics, and for every atom that makes up the world around us are nothing short of profound. In its simplest terms, proton decay is a theoretical process in which a proton, the positively charged particle that resides at the heart of every atomic nucleus, spontaneously disintegrates into smaller, lighter particles. The very idea challenges one of the most basic assumptions of physics, that the fundamental components of matter are permanent and indestructible. Within the framework of the standard model of particle physics, currently our best description of subatomic particles and their interactions, protons are considered completely stable. No experiment has ever caught a proton in the act of decay, and according to this model, it never should. Yet, beyond the standard model, a host of advanced theoretical frameworks suggests otherwise. One prominent example is the Grand Unified Theory, or GUT. This ambitious theory seeks to merge three of the four fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, into a single cohesive framework. Within this vision, protons are not immune to decay. They are incredibly long-lived, yes, but not eternal. Over timescales far exceeding the current age of the universe, a proton could spontaneously transform into other lighter particles. Physicists predict that when a proton decays, it would most likely produce a positron, the antimatter counterpart of an electron, along with a neutral particle known as a pion. This pion would not remain stable for long either, breaking down further into nearly massless particles such as photons or neutrinos. These products are capable of traveling immense distances through the cosmos without obstruction, a testament to the vast scale and delicate balance of subatomic processes. The decay process is staggeringly slow. For a single proton, even if you waited trillions of years, witnessing its disintegration would be highly unlikely. Scientists estimate that the half-life of a proton, the time required for half of a collection of protons to decay, could be on the order of 10 to the power of 34 years, a number almost beyond comprehension. To put that in perspective, the universe itself is approximately 1 followed by 10 zeros years old, roughly 13.8 billion years. This unfathomable disparity explains why proton decay has never been observed in laboratories under normal conditions. To overcome this challenge, researchers monitor vast quantities of protons simultaneously, vastly increasing the likelihood of detecting the rarest decay events. Detecting even a single instance would constitute a groundbreaking discovery in the annals of physics, revolutionizing our understanding of matter, energy, and the laws that govern them. A confirmed observation of proton decay would signify that the standard model is incomplete, pushing scientists toward new, more encompassing theories that could even pave the way to a theory of everything, a unified framework connecting all fundamental forces of nature. The implications stretch beyond theoretical physics into the very destiny of the universe itself. If protons decay, then over unimaginably long periods, all matter, from planets to stars, from galaxies to black holes, would eventually disintegrate into lighter particles and radiation. The universe, once teeming with structure, would become an empty expanse of fundamental particles drifting through space, a cold, silent void bereft of the atoms that form stars, planets, and life itself. Proton decay may also hold keys to other enduring cosmic mysteries. It could help explain the preponderance of matter over antimatter in our universe. Following the Big Bang, theory predicts matter and antimatter should have been created in equal amounts, annihilating each other. Yet matter dominates. Some physicists speculate that the subtle processes involved in proton decay might illuminate the origins of this imbalance. Detecting proton decay demands the most sophisticated instruments humanity has devised. Enormous underground detectors, often filled with tens of thousands of tons of ultra-pure water or other specialized materials, are engineered to capture the fleeting particles released by a decaying proton. These detectors must be shielded from cosmic rays and other sources of interference, buried deep beneath the Earth's surface. Examples include Super Kamiokande in Japan, a colossal tank holding 50,000 tons of water equipped with thousands of sensitive light detectors, and its successor, Hyper Kamiokande, currently under construction with even greater sensitivity. The Sudbury Neutrino Observatory in Canada and the Deep Underground Neutrino Experiment in the United States are similarly designed, initially to study neutrinos, but also capable of searching for the faint signs of proton decay. So far, no decay has been observed, but the search continues with unrelenting intensity. If a proton's fleeting demise were ever detected, it would stand as one of the most monumental scientific achievements of all time. Conversely, if no evidence of decay ever emerges, It would confirm that protons are indeed as stable as the Standard Model predicts, suggesting that matter, as we know it, may endure indefinitely. Either outcome reshapes our understanding of reality, but in the case of discovery, the revelation would be nothing less than cosmic in scale, redefining what we know about the permanence of matter and the ultimate fate of the universe itself. However, the absence of proton decay would send ripples through the foundations of modern physics, shaking the very assumptions of many advanced theories, such as grand unified theories. These frameworks, designed to merge the fundamental forces of nature into a single elegant picture, would require scientists to revisit their equations, reassess the relationships between particles, and possibly search for entirely new mechanisms to explain the hidden workings of the universe. The lack of proton decay would not merely be a minor anomaly. It would challenge the coherence of decades of theoretical work, forcing physicists to think beyond established paradigms and consider alternatives that might have been previously dismissed. For countless centuries, humans have looked up at the night sky, pondered their own mortality, and asked what happens after death. Across the globe, religions, philosophies, and spiritual traditions have grappled with this mystery. Many suggest that the essence of a person, the soul, does not simply vanish upon death. Instead, it continues in some form, often undergoing transformation and rebirth. This enduring belief, known as reincarnation, proposes that life is cyclical. The soul may inhabit new bodies, or perhaps traverse entirely different planes of existence in a continuous process of renewal. From the sacred texts of Hinduism and the philosophical teachings of Buddhism to the ancient mysteries of Egyptian and Greek thought, reincarnation is a concept deeply woven into the cultural and spiritual fabric of humanity. But what if this principle extends far beyond individual beings? What if the universe itself is subject to cycles of death and rebirth? This extraordinary notion, referred to as cosmic reincarnation, proposes that the universe does not end in a final, irrevocable collapse, but instead experiences a continual sequence of destruction and renewal. Philosophers and scientists alike have long contemplated whether the cosmos had a singular creation or if it exists in an eternal loop, endlessly cycling through phases of existence, collapse, and rebirth. Could the vast expanse of space, time, matter, and energy itself participate in a kind of reincarnation analogous to that of living souls? To explore cosmic reincarnation, one must first consider the birth of the universe as modern science understands it. Around 13.8 billion years ago, the universe began with the Big Bang, a cataclysmic event that generated space, time, and all matter. Over eons, galaxies coalesced, stars ignited, planets formed, and eventually life emerged. Yet, despite its astonishing complexity and apparent permanence, the universe is not static. Observations show that it is expanding, and a crucial question arises: will this expansion continue indefinitely, or will the universe eventually collapse, giving rise to another cosmic genesis? Among the theories that contemplate the ultimate fate of the cosmos is the Big Crunch. This scenario envisions a universe that does not expand forever but gradually decelerates, eventually reversing course. Over unimaginable spans of time, galaxies, stars, and planets would draw closer, converging into an infinitely dense point. In this collapse lies the potential for another Big Bang, a rebirth on a cosmic scale, a renewal of all existence. Extending this idea, the Big Bounce theory suggests that our universe may have already endured multiple cycles of expansion and contraction. Rather than a single beginning and end, the cosmos could be trapped in an eternal loop, where each Big Bang marks a new chapter in an infinite cosmic story. The idea of cyclical universes is not purely a product of modern physics. Across history, numerous cultures have described the cosmos as a repeating cycle. Hindu cosmology, for instance, envisions the universe undergoing continuous cycles of creation, preservation, and destruction. Each cosmic cycle, or kalpa, spans 4.32 billion years, after which the universe dissolves only to be recreated anew. In Buddhism, time is similarly perceived as cyclical rather than linear. Buddhist teachings describe worlds as constantly forming and disintegrating, mirroring the process of reincarnation at the level of human existence. Ancient Greek thinkers, including Heraclitus, contemplated the eternal flux of the universe, asserting that it was in a perpetual state of change and renewal. Stoic philosophers later posited that cosmic cycles of destruction and rebirth repeat indefinitely. Even Norse mythology recounts Ragnarok, a cataclysmic event in which the world is destroyed, only for a new one to emerge from the remnants of the old, echoing the theme of cosmic reincarnation. Modern science has revisited these ancient ideas through the lens of physics and cosmology. The cyclic model, developed by physicists such as Paul Steinhardt and Neil Turok, suggests that the universe undergoes an infinite series of expansions and contractions. Instead of originating from a singular Big Bang, the cosmos could have existed long before, destined to continue its cycle indefinitely. Quantum mechanics adds another layer of intrigue. At subatomic scales, particles appear and vanish in a seemingly endless process, hinting that the universe itself may operate under similar principles, undergoing perpetual cycles of creation and destruction. Even the second law of thermodynamics, which dictates that entropy, the measure of disorder, inevitably increases, might point toward cosmic reincarnation. When the universe reaches a state of maximum entropy, where energy is uniformly distributed and no work can be performed, some physicists theorize that a new universe could emerge from the resulting chaos, effectively resetting the cosmic cycle. One of the most tantalizing questions of cosmic reincarnation is whether a new universe would retain any memory of its predecessors. Human reincarnation is sometimes said to include recollections of past lives. Could the universe similarly preserve traces of its previous cycles? Some scientists speculate that structural patterns, cosmic formations, or even fundamental physical laws might persist across successive universes, providing a form of cosmic memory. If physical constants or the laws of nature remain consistent across cycles, this continuity could hint at an underlying rhythm, a hidden continuity connecting each birth, death, and rebirth of the cosmos. In this grand vision, the universe is not a singular event, but an eternal story, an unfolding narrative of death and renewal played out on a scale so vast that human comprehension strains to contain it. Each cosmic cycle is both an end and a beginning, a testament to the resilience and continuity of existence itself, reflecting, in the ultimate sense, the timeless principle of reincarnation writ across the fabric of the cosmos. Additionally, some researchers have proposed that the universe may carry subtle traces of its own ancient history, like a cosmic diary written across billions of light years. Patterns in the arrangement of galaxies, faint echoes of leftover radiation, or irregularities in the cosmic microwave background could all serve as faint fingerprints of previous cycles of existence. If detected, these traces would provide compelling evidence that the universe has undergone rebirths, not as a singular occurrence, but as part of an endless cosmic rhythm. The concept of cosmic reincarnation challenges everything we understand about existence. Life and matter would not be confined to a one-time event, but instead would exist as part of an eternal, unbroken cycle, stretching infinitely backward and forward. It raises profound questions about the universe's behavior across these cycles. Does each iteration of the cosmos follow the same blueprint, or do variations emerge with each rebirth? Could there be faint cosmic memories embedded in the very fabric of space and time, remnants of universes long vanished? If the universe itself can be reborn, might consciousness, in some form, also have existed before, transcending the boundaries of a single cosmic epoch? The idea of an endlessly reborn universe offers a certain philosophical solace, much like the spiritual concept of reincarnation, which suggests that life continues beyond the cessation of physical existence. Cosmic reincarnation implies that existence itself never truly ends. It does not vanish, it merely transforms, emerging anew in forms we can scarcely imagine. Imagine a distant future where civilizations scattered across the universe can no longer communicate, trapped in isolation as cosmic expansion pulls galaxies apart. Galaxies that once shimmered within view, accessible in theory by advanced technology, drift away so swiftly that no spacecraft, no signal, no particle of light could ever bridge the growing void. This is not the realm of science fiction. It is a consequence of the universe's relentless expansion, a concept cosmologists call the isolation of galaxies. According to this understanding, the universe's accelerating expansion will eventually place each civilization in its own gravitationally bound cluster, forever separated from all others. Even the most advanced civilizations would be confined to their cosmic neighborhood, unable to extend their reach beyond the invisible boundaries of their galaxy. Over 13,800,000,000 years ago, the universe burst into existence with the Big Bang, a cataclysmic eruption of energy and matter that set all cosmic motion into play. Galaxies began to form, stars ignited, and planets coalesced from clouds of gas and dust. Yet amid all this creation, one defining feature of the universe emerged. Its expansion never ceased. In the 1920s, Edwin Hubble observed that galaxies are not static. They are fleeing from one another, and the more distant a galaxy, the faster it recedes. Space itself is stretching, carrying galaxies along with it. Initially, scientists believed that gravity might slow this expansion, perhaps even reverse it someday. But in the 1990s, studies of distant supernovae revealed a startling truth. The universe's expansion is accelerating. The driving force behind this acceleration is dark energy, a mysterious entity constituting nearly 70% of the universe's total energy. Dark energy continuously pushes galaxies apart, a force so pervasive that it will eventually render vast stretches of space unreachable. Today, this acceleration is noticeable only across the largest cosmic scales. Galaxies bound together by gravity, such as the Milky Way and Andromeda, remain within reach. But in the distant future, the cosmic landscape will transform dramatically. As dark energy persists in driving expansion, only galaxies within the same gravitational clusters will remain observable to each other. Beyond that, everything else will recede faster than light itself can travel, vanishing forever from view. Scientists predict that in roughly 100 billion years, every galaxy outside the local group will be completely inaccessible. Civilizations, no matter how advanced or resourceful, will have no hope of reaching or even observing them. The universe will appear, to those future observers, as a lonely expanse with only their galaxy in sight. To visualize this, picture standing on a beach and watching distant islands across the horizon. As the ocean stretches and surges, those islands drift away faster than any boat or swimmer could traverse. Eventually, they disappear entirely from view, leaving only endless water. Replace the ocean with the cosmos and the islands with galaxies, and the analogy becomes chillingly accurate. The isolation of galaxies has profound implications for intelligent life. In today's universe, light and radio waves from faraway galaxies allow us to glimpse civilizations and cosmic events billions of years in the past. But when galaxies cross the cosmic event horizon, even the ancient light they emit will never reach any observer. For astronomers in the Milky Way, 100 billion years from now, the sky will be empty. The evidence of countless galaxies will vanish, leaving a universe that seems confined to a single galaxy. Even if these future civilizations attempted intergalactic communication or travel, space itself would expand too rapidly for success. Each galaxy would become a self-contained island, forever isolated in the cosmic sea. Humanity, or any intelligent life that endures into this distant era, would confront unique existential challenges. The perspective of civilizations may shift, leading them to believe that their galaxy is the entirety of existence. Without knowledge of the wider universe, myths and ancient records from prior eras could be dismissed as fanciful tales. Resource management would become a central concern. Deprived of intergalactic trade or expansion, life would be confined to the materials and energy within a single galaxy, requiring careful stewardship of planets, stars, and other resources. Civilizations might turn inward, focusing on technological advancement, cultural evolution, and understanding their immediate surroundings. Some may see isolation as a puzzle to overcome. Others may accept it as the inevitable march of cosmic evolution. Over trillions of years, even the stars of the Milky Way will fade and die. Star formation will slow as intergalactic material ceases to replenish the galaxy, leaving a colder, darker, and increasingly inhospitable universe. The cosmic event horizon, the ultimate boundary of causality, dictates the maximum distance from which information, in any form, can reach an observer. Like a ship disappearing beyond the horizon on a vast ocean, galaxies beyond this threshold vanish from the observable universe. Today, we can still observe countless distant galaxies because their light continues to traverse space. In the far future, however, this will no longer be possible. and civilizations will be left with a universe that feels at once immense and remarkably empty. However, as the universe continues its relentless expansion, an invisible boundary known as the cosmic event horizon slowly creeps closer to distant galaxies. Galaxies that lie far enough away will inevitably pass beyond this horizon, a point of no return after which their light, no matter how bright or energetic, will never reach us again. Our most advanced telescopes, capable of peering billions of light years into the past, will be powerless to reclaim their vanished signals. From our vantage point, these galaxies will not vanish suddenly. Instead, they will gradually dim, fading like the last embers of a dying fire until they are completely erased from the night sky. Trillions upon trillions of years from now, long after the universe has aged far beyond recognition, the only galaxies left visible to us will be those within our own local group. A modest cluster containing the Milky Way, Andromeda, and a few dozen smaller companion galaxies. Beyond this intimate cosmic neighborhood, every other galaxy will be lost to the void, forever unreachable and invisible. This inevitable isolation has profound implications. If intelligent life exists somewhere in those far-flung galaxies, there will come a time when all communication becomes impossible. No radio signal, no quantum message, no technology could ever bridge the ever-widening gulf between us. The thought of civilizations permanently isolated in their own islands of stars raises haunting questions. Imagine for a moment a distant civilization residing in a galaxy billions of light years away. Today, they might gaze at the heavens and see a universe awash with countless galaxies, each twinkling with the light of billions of stars. But in the distant future, their sky will transform. One by one, those galaxies will vanish, leaving only the faint glow of their own galaxy, a solitary cluster drifting in a featureless darkness. Even with telescopes far beyond our current imagining, they would see nothing but emptiness beyond their cosmic horizon, trapped in a self-contained universe that offers no evidence that anything else ever existed. This possibility invites a chilling reflection. Could we ourselves already live in such a universe? Perhaps countless galaxies have already slipped beyond our own cosmic horizon, leaving us unaware of their former brilliance. The notion is sobering, highlighting the fragility of our observational window and the limits of our knowledge about the cosmos. As the universe ages, galaxies will become more isolated, and the tapestry of cosmic connections that once linked them will unravel. The long-term fate of the universe remains uncertain, but scientists have outlined several dramatic scenarios, each more awe-inspiring and terrifying than the last. One possibility, known as the Big Freeze, envisions a universe in which dark energy continues to accelerate expansion indefinitely. Galaxies would drift ever farther apart, and stars would burn out one by one, leaving behind cold, lifeless remnants. Eventually, only black holes and dead stars would punctuate the void, a silent cosmos devoid of light or motion. Another scenario, the Big Rip, imagines dark energy growing so powerful that it literally tears galaxies, stars, planets, and even atoms apart. In this vision, the universe would end in a violent burst of energy, a cosmic unraveling so complete that nothing recognizable would remain. The Big Crunch, by contrast, envisions a reversal of expansion. Gravity would pull the cosmos back into itself, collapsing all matter and energy into a singular point, perhaps setting the stage for a new Big Bang, a rebirth of the universe in a never-ending cycle. Regardless of the scenario, one certainty persists. The isolation of galaxies is unavoidable. Over unimaginable spans of time, the cosmic landscape will grow lonelier, and the invisible bonds that once connected distant clusters of stars will vanish forever. For centuries, humanity has wrestled with questions about the nature of the universe. Does it stretch infinitely, beyond the reach of comprehension? Or does it possess an ultimate endpoint, a moment where all that exists ceases to be? This tension between the infinite and the finite has fascinated scientists, philosophers, and theologians alike, creating a paradox as profound as it is unsettling. The idea of infinity itself is almost incomprehensible, a universe with no edges, no boundaries, no terminus. To travel through space in such a universe would be to journey forever, with no final wall to mark the end. Yet modern science confronts us with evidence that our cosmos may indeed have a limit, or at least a defined fate. The notion of an infinite universe traces back to ancient civilizations. Greek philosophers such as Anaximander and Democritus speculated that the cosmos might extend endlessly, filled with infinite stars and worlds. But it was only with the advent of modern physics that the concept gained rigorous scientific credibility. Today, the theory of cosmic inflation supports the possibility of an infinite universe. According to this theory, the universe expanded at unimaginable speeds in the first fractions of a second after the Big Bang, potentially without bounds. The uniform distribution of galaxies observed across the sky adds weight to this idea. Astronomers see no sign of a cosmic edge, no evidence of a boundary. The faint, uniform glow of the cosmic microwave background, the afterglow of the early universe, seems to stretch on indefinitely, further suggesting boundlessness. The theory of parallel universes, or the multiverse, extends this notion even further, positing that our universe might be just one of countless others in an infinite cosmic expanse, each with its own laws of physics, its own dimensions, and its own histories. Yet alongside these arguments for infinity stands the stark reality of an eventual cosmic end. The contradiction between an endless universe and a universe with a finite destiny is one of the most intriguing puzzles in modern cosmology. Among the theories for the universe's ultimate fate, heat death stands out. Rooted in the second law of thermodynamics, heat death envisions a future where all energy is evenly spread, leaving no gradients for work or motion. The universe would become a frozen, inert void, an eternal darkness where nothing occurs. The Big Crunch offers another vision. If expansion slows and reverses, all matter and energy would collapse into a singularity, mirroring the conditions before the Big Bang, suggesting a cyclical universe of birth, collapse, and rebirth. The Big Rip, more violent still, imagines a universe torn apart atom by the unstoppable force of dark energy, leaving nothing behind. Quantum decay introduces yet another possibility, a sudden, unpredictable collapse caused by changes in the fundamental nature of space itself, erasing all existence instantaneously. At first glance, the concept of an infinite universe seems incompatible with these visions of an end. Yet physicists have proposed ways to reconcile the two. Infinity in space does not necessarily imply permanence in time. A universe might extend endlessly while still evolving, changing, and eventually reaching a state of quiet desolation or dramatic collapse. Quantum mechanics introduces another nuance, suggesting that space and time are flexible in constant flux. As one universe fades, another might emerge elsewhere, a notion tied to the multiverse hypothesis. In this framework, the destruction of one universe is not final. It becomes the seed for new realities, an infinite cycle of creation and annihilation continuing without end. The cosmos, in its vastness and mystery, challenges every instinct of the human mind. Galaxies fade, stars die, and entire civilizations may vanish without ever knowing they were part of a grander cosmic story. Yet even as isolation spreads and darkness encroaches, the universe's infinite potential, its capacity to generate new realities, new galaxies, new wonders, remains a testament to the profound and unfathomable scale of existence. Time stretches forward, galaxies drift apart, and we are left to ponder our place in a universe simultaneously finite in fate and infinite in possibility. Additionally, if time itself is not a fundamental building block of reality, but rather an emergent phenomenon, then the notion of an ultimate end may be far less absolute than it appears. Some scientists theorize that at the deepest layers of existence, time might not progress in a simple linear fashion, but instead, what we perceive as beginnings and endings could be fluid, and the concept of a final moment might simply signify a transformation into an entirely different form of reality beyond human comprehension. Beneath the complex mathematics and advanced scientific frameworks, this possibility carries profound philosophical and emotional weight. Humans are creatures bound by finite experiences. We are born, we grow, we live, and we die. Every event we know has a beginning and an ending. To imagine a universe that stretches endlessly is almost inconceivable, just as it is equally difficult to comprehend the notion of absolute cessation, a complete void where existence ceases entirely. This paradox also casts a spotlight on humanity's place in the vast cosmos. If the universe is infinite, does it render human life insignificant, merely a brief flicker in an endless expanse? Or does it amplify the wonder of our existence, highlighting life as an extraordinary anomaly in a sea of eternal continuity? Conversely, if the universe is destined to end, What consequences would that hold for all we have created, discovered, and treasured over millennia? These questions intersect with both scientific inquiry and spiritual reflection. Across cultures and religious traditions, humans have long sought meaning in the cosmos, often envisioning the universe as possessing a divine origin and ultimate purpose. Other philosophies propose an existence enmeshed in cycles beyond human understanding, where beginnings and endings are merely moments in an eternal rhythm. Whether through science, philosophy, or faith, humanity's quest to understand the ultimate nature of reality has persisted for thousands of years. From the earliest astronomers of ancient civilizations who charted the stars and pondered the heavens, to modern physicists unraveling the subtle fabric of space-time, human curiosity has never faltered. As our understanding deepens, we encounter concepts that challenge every assumption about reality. Exotic physics is one such frontier, a realm where the known laws of nature bend and sometimes shatter, giving rise to phenomena that once belonged solely to the realm of imagination. In this pursuit, scientists approach what some call the endgame of discovery, a point at which the ultimate laws governing the universe could be fully understood, granting humanity unparalleled insight and potential influence over the cosmos. Exotic physics encompasses theories and experimental frontiers that extend beyond classical physics. While Newtonian mechanics and Einsteinian relativity explain much of the observable world, exotic physics ventures into territories that appear almost otherworldly. This includes concepts such as negative energy, extraspatial dimensions, wormholes, and the tantalizing possibility of parallel universes. Some of these ideas remain purely theoretical, expressed through abstract equations awaiting experimental confirmation. Yet advances in quantum mechanics, particle physics, and astrophysics are increasingly suggesting that reality is far stranger and more intricate than previously imagined. When physicists refer to the endgame, they describe the pursuit of ultimate comprehension, a stage in which humanity might fully decode the fundamental laws of nature, potentially unlocking capabilities once deemed impossible. The endgame is not inherently catastrophic. It is not about destruction, but about the potential mastery of natural forces, or the confrontation with challenges beyond human capability. Many believe that the discoveries of exotic physics will be pivotal in this stage. If humanity can harness its secrets, we may unlock technological breakthroughs that could enable time travel, exploration of other dimensions, or access to seemingly limitless energy. Failure, however, could leave us bound by the limits of our current understanding, unable to advance beyond the confines of our present knowledge. Among the most captivating propositions in exotic physics is negative energy. Unlike ordinary energy, which powers everything from light bulbs to rocket engines, negative energy exhibits bizarre properties, including the ability to warp space and time. Physicists have speculated that negative energy could form the basis of a warp drive, a propulsion system capable of faster-than-light travel. Such technology could allow humanity to traverse the vastness of space in a fraction of the time otherwise required. The concept was first seriously explored in the early 1990s by physicist Miguel Alcubierre, who theorized that a bubble of warped space could push a spacecraft forward at superluminal speeds without violating Einstein's relativity. If realized, this could usher in an era of interstellar exploration, enabling human colonization of distant planets and potential encounters with extraterrestrial civilizations. Yet if negative energy remains inaccessible, humanity may remain confined to the narrow bounds of our cosmic neighborhood. Wormholes present another mind-bending concept in exotic physics. These theoretical structures act as shortcuts through space-time, connecting distant points in the universe almost instantaneously. First theorized by Albert Einstein and Nathan Rosen in the early 20th century, wormholes remain hypothetical, with no naturally occurring examples discovered. They tantalize with the possibility of near-instantaneous cosmic travel, a means of bypassing the vast distances that would otherwise take millennia to traverse. If harnessed, wormholes could revolutionize human understanding of space, time, and the very nature of reality itself. However, some researchers propose that if humanity could somehow create or stabilize a wormhole using exotic matter, an unusual and hypothetical form of matter with properties opposite to those we encounter in everyday life, we could completely transform the nature of space travel as we know it. Imagine leaving behind the constraints of conventional propulsion, where journeys to even the closest star systems take decades, centuries, or longer. Instead, a spacecraft could enter a wormhole and emerge on the other side of the galaxy in mere seconds, as if the vast distances of space were compressed into a single traversable shortcut. In the grand scheme of cosmic exploration, wormholes represent a tantalizing endgame. They suggest a future where distance is no longer an obstacle, where the stars are not unreachable points of light, but destinations waiting to be visited. Yet, if wormholes remain confined to equations and theoretical models, interstellar travel may remain an aspiration forever beyond our reach, a dream that teeters on the edge of imagination and possibility. One of the most astonishing and mind-bending concepts emerging from exotic physics is the possibility of a multiverse. Instead of the singular universe we perceive, there could be an infinite expanse of parallel realities, each existing alongside our own, yet inaccessible through conventional means. Some scientists argue that every decision, every choice, every small divergence in our lives may spawn a new branch in reality, leading to an unimaginable number of alternate versions of ourselves scattered across countless universes. Others speculate that entirely separate universes may exist beyond our own, governed by physical laws that could be radically different from those we experience. Universes where matter, energy, and even the concept of time operate in ways that defy our comprehension. If the multiverse is real, it would not merely expand our understanding of reality, it would fundamentally reshape it. Some theories even suggest that advanced civilizations in these parallel universes may have already discovered methods to traverse between realities. This raises a profound question: could humanity follow suit? If we eventually unlock the means to navigate the multiverse, the ultimate endgame could see humanity no longer confined to a single cosmic neighborhood, but exploring realms of existence previously unimaginable, venturing into dimensions that challenge every assumption about life, reality, and the very nature of consciousness. Time travel is another possibility lurking at the frontier of exotic physics. While many scientists remain skeptical, dismissing it as impractical or impossible, some theoretical frameworks suggest that under highly specific conditions, time travel could be achievable. One of the primary obstacles is the paradoxes it introduces. The most infamous example is the grandfather paradox. If someone travels back in time and prevents their grandfather from meeting their grandmother, their own birth would be negated. If they were never born, how could they have traveled back in time to interfere with history in the first place? Certain physicists suggest that parallel timelines or self-correcting timelines could resolve these contradictions, potentially allowing time travel without unraveling causality. Mastering time travel would open doors to unimaginable possibilities, witnessing historical events firsthand, averting disasters before they occur, and exploring the flow of history in ways that could revolutionize human understanding of cause and effect. Yet with these extraordinary prospects come equally extraordinary risks. Exotic physics, by its very nature, operates at the edge of comprehension, and meddling with forces we barely understand could have catastrophic consequences. One of the most frightening scenarios is a false vacuum collapse. Theories suggest that our universe exists in a stable energy state, but if it were suddenly forced into a lower energy state, the transition could destroy everything instantaneously. Experiments with exotic physics, conducted without full knowledge or caution, could inadvertently trigger such a collapse, potentially obliterating not just Earth, but the entire cosmos as we know it. If humanity eventually learns to travel across galaxies or communicate across dimensions, the implications extend beyond physics to contact with intelligent extraterrestrial life. Such encounters could be exhilarating or perilous. Some advanced alien civilizations might regard us with indifference, while others could see humanity as insignificant or even as a threat. Reaching out without careful preparation might invite dangers we are not equipped to handle. Furthermore, tampering with the fundamental fabric of reality, whether through wormholes, time travel, or interdimensional exploration, could generate unintended consequences, subtly or catastrophically altering the natural order of the universe. The potential effects are unpredictable, ranging from minor disruptions in physical laws to universe-scale calamities. The path forward is exhilarating, yet fraught with unknown perils, challenging humanity to balance ambition with caution as we push the boundaries of what is physically and conceptually possible. Humanity stands at the threshold of a cosmic frontier where the extraordinary ideas of exotic physics, wormholes, multiverses, time travel, and reality manipulation offer both the promise of unprecedented exploration and the threat of irreversible catastrophe. Each theoretical breakthrough could bring us closer to reshaping existence itself, but each misstep could unravel the delicate tapestry of the cosmos. In this precarious dance between ambition and caution, the endgame is both thrilling and terrifying, a universe where distance, time, and even reality itself are no longer immutable, yet where the stakes of experimentation could literally be everything.